Power in the universe shows itself in many different ways. Some forces destroy everything they touch, others quietly keep the universe in balance. And then there are those that are so unusual, so extreme, that scientists still cannot fully explain how they work. These are the forces that stretch the very limits of reality itself. What is the most powerful object in the universe? Could it be a supernova, exploding so brightly that it outshines a whole galaxy for a short time? Or is it a black hole, twisting space and time into impossible shapes? In this video, we'll dive into forces that stretch reality to its very limits. Before we begin, let us know where in the world you're watching from and what time it is there for you now. So, settle in and get ready for a ride to the most powerful object in the universe. Ultra-high energy cosmic rays are nature's own particle accelerators, and they are far more powerful than anything human beings have ever built. From time to time, a single particle, smaller than an atom, slams into Earth with more strength than a baseball hurled by a world-class pitcher. These rare visitors are among the most powerful subatomic particles ever detected. Unlike stardust or solar wind, they do not arrive in clouds or streams. Instead, each one comes alone, like a silent microscopic bullet fired from the depths of space. These particles travel unimaginable distances, wandering across the universe until, by chance, they reach our planet. When they do, they sometimes unleash more energy than any human-made machine has ever produced. To grasp just how extraordinary that is, consider the Large Hadron Collider in Switzerland, the most advanced particle accelerator on Earth. This machine smashes protons together at nearly the speed of light, creating energies of up to 13 trillion electron volts. That is already an astonishing amount of energy concentrated into a single particle, enough to allow scientists to probe the fundamental building blocks of matter. Yet ultra-high energy cosmic rays make those numbers seem tiny. Some of them carry energies greater than 100 quintillion electron volts. That is millions of times more energy than the most powerful accelerator ever built by human hands. Imagine such force being compressed into something smaller than a proton. It almost seems impossible, and yet nature makes it real. Most ordinary cosmic rays are born in events such as solar flares or exploding stars. They are common and relatively low in energy. But these ultra-powerful rays are different. They do not appear to come from anywhere nearby. Instead, they must have been launched from violent, distant corners of the universe, perhaps from supermassive black holes that spin in the hearts of galaxies, twisting space itself and hurling out colossal jets of particles. Another possibility is that they are linked to gamma-ray bursts, the fierce and brief explosions left behind when stars collapse or collide. Despite decades of searching, scientists have only observed a handful of these extreme rays. Their journeys are distorted by magnetic fields that bend their paths, making it nearly impossible to trace them back to their true sources. They do not strike Earth's surface directly. Instead, they smash into atoms high in the atmosphere, shattering them and creating a chain reaction, a great shower of secondary particles that spreads across kilometers of sky. To study these showers, scientists build vast observatories on the ground. One of the largest is the Pierre Auger Observatory in Argentina, which uses enormous networks of detectors spread across wide plains. When a cosmic ray slams into the atmosphere, it sends a wave of particles cascading downward. The detectors measure this wave, studying its size and shape, much like reading the ripples in a pond to figure out what kind of stone caused the splash. From those ripples, researchers try to calculate the energy and nature of the original cosmic ray. Even with all this effort, ultra-high energy cosmic rays remain incredibly rare. On average, only one strikes each square kilometre of Earth's surface in an entire century. A person could watch the sky for their entire lifetime and never witness one. Yet, if we can understand them, they could reveal secrets about the most extreme environments in the universe. They might even uncover new laws of physics. Some scientists believe that if space itself has a hidden structure at the smallest scales, these cosmic rays could help us detect it. Human machines like the Large Hadron Collider represent the very peak of what we can achieve, and they are indeed powerful. But when compared to nature's mysterious accelerators, they seem almost small. Somewhere, in the deep void between galaxies, something is hurling single particles with unimaginable force across distances so vast that the mind struggles to comprehend them. These lone travelers remind us that the universe still hides powers far beyond our reach, waiting to be understood. In the silent depths of space, there exist two very different kinds of cosmic messengers. On one side are the invisible particles of ultra-fast cosmic rays, tiny specks smaller than atoms, darting through the universe unseen. On the other side are the giants, mega-asteroids, vast mountains of stone and metal that drift like sleeping titans, and when one of these titans slams into Earth, the result is nothing short of apocalyptic. A single asteroid 10 kilometers wide carries more destructive power than every nuclear weapon ever built by humankind, not just once, but many times over. The science behind it is chillingly simple. Anything that moves at enormous speed stores up energy, kinetic energy. And when an object as massive as an asteroid suddenly stops by crashing into Earth's crust, all that energy has to go somewhere. The result is like a hammer blow against glass, only on a planetary scale. The ground shudders violently, rocks fracture and split apart, the crust melts into liquid fire, shock waves rip through the layers of Earth, cracking the surface for hundreds of kilometers around. In only seconds, a crater is gouged into the planet, deeper and wider than anything human beings have ever dug. But the crater is only the beginning. The energy released is so immense that forests for thousands of kilometers ignite instantly. Winds roar outward at hurricane strength, not created by weather, but by the sheer blast of the impact. Dust, ash, and shattered rock are hurled high into the sky. When they fall back, they heat the atmosphere so fiercely that the very air becomes an oven. Animals caught in the open perish in moments. If such a rock crashes into the ocean, the destruction grows even more terrifying. Because most of Earth is covered by water, this is the more likely scenario. The strike would throw up monstrous waves, far taller and faster than any tsunami caused by earthquakes. These water walls would cross whole oceans, smashing into coastlines on the other side of the planet hours later. Towns, cities, and even mountain valleys near the shores would be obliterated. In such a disaster, the ocean itself becomes a weapon. Then comes the darkness. Dust and soot from the blast spread across the atmosphere, blocking sunlight for months, sometimes years. This artificial winter is not made of snow and ice, but of cold shadows. Plants wither without light. Herbivores starve. Carnivores follow soon after. Food chains collapse. Whole ecosystems vanish in silence. We know this nightmare is not just imagination, because it has already happened. About 66 million years ago, an asteroid around 10 kilometers wide crashed into what is now the Yucatan Peninsula in Mexico. The scar of its landing, the Chicxulub crater, is still there today, stretching more than 180 kilometers across, hidden beneath layers of rock and sediment. That single impact ended the age of dinosaurs. 75% of all species alive at the time vanished forever. The Earth became almost unrecognizable within only a few short years. Those that survived were the small, the adaptable, and the fortunate. The planet eventually healed. The skies cleared, warmth returned, and life began again in new forms. But the price was enormous, and this wasn't the only blow Earth has suffered. Over the ages, smaller asteroids, some only a few kilometers wide, others even less, have struck our world, leaving behind craters, shattered rocks, and strange minerals that tell the story of their fiery arrival. Even now, scientists are still finding new craters hidden in deserts, tundras, and jungles. These scars remind us that asteroid strikes are not relics of a distant past. They remain a threat today. Modern researchers use powerful telescopes to watch the heavens, scanning for any incoming rocks. Yet space is vast and black, and asteroids are faint, reflecting only a whisper of sunlight. Many slip by unnoticed until they have already passed us. Large ones are easier to track, but even then, our warning time might be short, sometimes only months, maybe even less. Plans are being drawn up to defend the Earth. Some scientists imagine rockets that could nudge an asteroid off its path. Others speak of solar sails or even controlled nuclear blasts to shift its course. But these are still theories, experiments on paper and in simulations. Humanity has never yet faced the need to use such defenses in a real crisis. And even with years of warning, success is far from certain. Against a rock 10 kilometers wide, all we can hope for is to deflect it, not destroy it. Yet as frightening as they are, asteroid impacts are also part of Earth's story of creation. Some scientists believe that long ago, asteroids brought water and organic molecules to our young planet, perhaps even sowing the seeds of life itself. In their destruction, they have also created. Craters can become lakes, homes for new ecosystems. Impact sites can expose minerals hidden deep in the crust. Still, these cosmic hammers follow no rules. They do not care about our cities, our histories, or our dreams. One day, without warning, a new giant could arrive. Fast, heavy, unstoppable. And when it does, the Earth, mighty as it is, would tremble under the full crushing force of a single rock from the cold darkness of space. Far beyond the familiar glow of our sun, in the silent darkness between the stars, there are lonely worlds that wander without a home. These are rogue planets, giant spheres of rock, ice and gas that have been flung from their birthplaces and left to drift endlessly through the galaxy. They are worlds without warmth, cut off from the fire of a parent star. Some may be frozen solid on the surface, cloaked in layers of eternal ice, while deep inside they still carry the leftover heat of their violent creation. These wandering giants move silently, crossing the empty gulf of space like ghostly ships in an endless night. Most of the time, they travel unnoticed. Yet sometimes, just sometimes, their paths bring them dangerously close to other planetary systems. The odds of a direct collision are very small, but not zero, and if one of these orphaned worlds were to smash into another planet, especially one the size of Earth or even larger, the outcome would be beyond imagination. A collision between planets is nothing like a rock striking another rock. These are entire worlds, spheres of metal and stone wrapped in gravity, molten cores, atmospheres, and perhaps even life. When two such bodies are pulled together by gravity and collide, the event is not merely an impact. It is a cosmic upheaval, powerful enough to reshape an entire star system. Imagine for a moment one such rogue planet. Perhaps it's the size of Earth, or maybe as large as Jupiter. It has been wandering the galaxy for billions of years, cloaked in darkness, with no sunrise and no sunset. Its surface is frozen, its oceans locked in ice, but deep below lies the slow heartbeat of heat from its birth. Now imagine this world straying too close to another planet. Gravity begins its patient pull. At first, they drift slowly toward each other, but as the distance shrinks, their pace quickens. What began as a slow dance becomes a headlong rush. At the instant of impact, the violence unleashed would dwarf every weapon and explosion humanity has ever known. The energy released would be more than 1 trillion times greater than the mightiest nuclear bomb ever built. In a heartbeat, mountains would flatten, oceans would boil into steam, and atmospheres would be blasted outward into space. The very crust of both planets would tear apart. Their molten cores, dense and glowing, would collide and possibly fuse into one. Shattered rock, liquid fire and hot plasma would spray across space. For a brief blinding moment, the crash could shine brighter than many stars. Now picture if such a collision happened with an inhabited world, a planet like Earth, full of forests, oceans, cities and life. There would be no warning siren loud enough, no shelter strong enough, no escape possible. The strike would not just destroy civilizations, it would erase continents, vaporize oceans, and possibly rip apart the planet itself. Life would not simply die, it would vanish, erased in fire and chaos. Yet from destruction comes transformation. The shattered remains of the colliding worlds could fuse together, becoming a brand new planet. It would be a molten sphere, spinning rapidly, its surface a boiling ocean of liquid rock. Around it, clouds of debris would swirl in orbit. Over millions of years, these fragments could gather into rings or form new moons. Slowly, painfully, the heat would fade. Over eons, the molten chaos would cool, and in time, a new planet might emerge, reshaped, rebuilt, and perhaps ready to cradle life once more. Though we cannot witness such collisions happening in real time, they unfold too slowly and too far away. We see the scars they have left behind. Earth itself carries the memory of one. Long ago, when Earth was young, a planet about the size of Mars, often called Theia, is believed to have struck it with unimaginable force. The impact ripped away a massive portion of Earth's outer layers, flinging the debris into orbit. Over time, that debris gathered into the sphere we now know as the Moon. Earth survived, but it was forever altered. Its tilt, its spin, and even its seasons shaped by that ancient crash. Over time, that debris gathered into the sphere we now know as the Moon. Earth survived, but it was forever altered. Its tilt, its spin, and even its seasons shaped by that ancient crash. Other worlds in our solar system show similar wounds. Uranus, tilted dramatically on its side, may have been knocked over by a giant impact. Mercury, with its oversized metallic core and thin crust, may have lost much of its rocky shell in a colossal collision long ago. These quiet scars remind us that planet-shattering events are not just theories, they are the building blocks of solar systems. Scientists believe that rogue planets are far more common than we once thought. There may be as many rogue planets in the Milky Way as there are stars, billions of dark, wandering worlds, some the size of Earth, others as massive as Jupiter. Even without striking another planet, their presence is dangerous. A rogue world passing close to a star system could tug planets out of orbit, disturb comets, or hurl asteroids toward inner worlds. Moons could be pulled free, orbits could be twisted, and whole systems could be thrown into chaos. But if one of these wayward planets collides, that is no mere dent in the cosmic order. It is a reset button, wiping the slate clean and giving rise to something new. When most people hear the word supernova, they usually imagine the classic kind, the mighty death of a massive star. In that familiar version, a giant star at least 10 times heavier than our Sun builds up a dense iron core. Once the iron core grows too heavy to hold up the crushing weight of the star above it, gravity takes over. In less than a single second, the core collapses. The star's outer layers rush inward, slam into the collapsed core, bounce off, and then blast outward in a titanic explosion that can outshine entire galaxies. That is the textbook picture of a supernova. But there exists another kind, one that is quieter, rarer, and stranger. It does not come from the biggest stars, nor does it rely on iron. Instead, it is born from stars of medium size, not small enough to fade gently into white dwarfs, but not large enough to go out in the traditional violent supernova. These stars, usually between 8 and 10 times the mass of our Sun, die in a unique way that astronomers are only now beginning to understand. This mysterious process is called an electron capture supernova. In such stars, the core does not fill with iron. Instead, it is built from lighter elements such as oxygen, neon, and magnesium. For millions of years, the star lives in relative quiet, fusing lighter elements into heavier ones, slowly feeding its growing core. But one day, something strange begins to happen inside that dense heart. Electrons, the tiny particles that normally buzz around atoms and help carry energy, start to vanish. They are pulled into the very nuclei of atoms, where they combine with protons and form neutrons. This transformation, known as electron capture, quietly changes everything. Electrons are crucial because they provide pressure that pushes outward against the force of gravity. When enough of them disappear, that supportive pressure crumbles. With nothing left to resist, gravity wins. The collapse happens suddenly. The core falls in on itself, squeezing tighter and tighter, until neutrons are packed together more densely than in any other place in the universe. The outer layers of the star rush inward, smashing into the neutron-rich core. In that instant, the collapse reverses. The shock wave blasts outward, tearing the star apart in a hidden but mighty explosion. Electron capture supernovae are not as blindingly bright or as violent as the iron core supernovae, but they carry secrets of great importance. They may explain how certain rare isotopes are spread across galaxies. They may shed light on how stars formed in the early universe and why some ancient stars hold chemical fingerprints that ordinary supernova cannot explain. Finding these events, however, is extremely difficult. They are rare, and when they occur, they can easily be mistaken for other kinds of supernovae. Only by studying them closely can astronomers spot the subtle differences. Their light curves, the way brightness changes over time, tend to fade a little more slowly. Their spectra, when broken down with powerful instruments, reveal unusual chemical patterns, hints of oxygen, neon, and magnesium that betray their strange origin. Now, with new telescopes scanning the skies and better models guiding predictions, researchers are finally uncovering these hidden deaths. Electron capture supernovae are proving to be a special bridge between quiet stellar endings and violent ones. They may explain why some neutron stars, those dense city-sized remnants left behind, have very specific masses, weaker magnetic fields, or slower spins compared to the dramatic neutron stars formed in iron core explosions. Even more intriguingly, the shockwaves from these quieter explosions may help trigger the birth of new stars by rattling nearby clouds of gas. In this way, electron capture supernovae may play an unsung role in the grand recycling of matter, spreading elements like oxygen and magnesium across the cosmos to seed future generations of stars and planets. But these explosions walk a razor-thin path. If the star is too massive, it will end as a classic iron core collapse. If it is too small, it will fade gently into a white dwarf. Only stars that fall into a very narrow mass range, with just the right core composition and just the right timing of electron capture, can end in this quiet catastrophe. Electron capture supernovae may be subtle compared to their louder, brighter cousins, but they reveal an essential truth of the universe. Even the quietest endings can leave behind legacies that echo across the stars. Some stars are born so enormous, so hot and so bright that they defy the usual rules of stellar death. These giants, weighing anywhere from dozens to several hundreds of times more than our Sun, live fast and die young. Their lifespans are measured not in billions of years like smaller stars, but in only a few million years at most. And when their time comes, their deaths are unlike almost anything else in the universe, so violent, so absolute, that nothing is left behind. Most stars end when their fuel runs out or when their iron cores collapse under their own weight. But for a rare few of these titans, death comes for an entirely different reason. They do not explode because they are weak. They explode because they are too strong. They destroy themselves from the inside out in a cataclysm called a pair instability supernova. To understand this, we must journey into the fiery heart of one of these monsters. At its centre, the temperature climbs to hundreds of millions of degrees. Here, lighter elements are steadily fused into heavier ones. Hydrogen fuses into helium. Helium becomes carbon. Carbon fuses into oxygen, and so on. With each new stage of fusion, more energy bursts outward, balancing the crushing inward pull of gravity. This balance of forces, the outward push of heat against the inward weight of the star, is what keeps the star alive. But in the most massive stars, things take a strange and dangerous turn. When the core temperature climbs to billions of degrees, the very light that usually supports the star begins to act differently. Instead of simply pressing outward as radiation, the high-energy photons start changing form. They transform into pairs of particles and their mirror opposites, electrons and positrons. When light itself becomes matter and antimatter, it stops holding up the star. The radiation pressure drops. Gravity, patient and merciless, seizes its chance. The balance shatters. The core contracts. Pressures mount higher and higher. Then, in less than an instant, the entire star erupts in a runaway chain of fusion reactions. Unlike a typical supernova, which first collapses before it explodes, a pair instability supernova detonates immediately. Oxygen, neon, and other heavy elements fuse all at once, releasing a flood of energy so vast that the entire star is torn apart from within. Nothing survives. No neutron star, no black hole, only a vast cloud of gas and elements expanding into space at thousands of kilometers per second. This is one of the only known ways for a star to die, leaving behind absolutely nothing. No remnant, no collapsed corpse, just matter scattered across the cosmos. And the cause is astonishing. The star's own light turns against it. The more massive the core becomes, the hotter it gets. The hotter it gets, the more photons transform into particles. The more particles appear, the weaker the radiation pressure becomes. The weaker the pressure, the faster gravity takes over. It is a deadly feedback loop that ends in complete destruction. These cosmic fireworks are rare. They only occur in stars of very particular sizes, somewhere between 130 and 250 times the mass of the Sun. If the star is smaller, it may survive, at least for a time. If it is larger, its collapse may skip the explosion entirely and plunge straight into becoming a black hole. When they do happen, pair instability supernovae enrich the universe in a unique way. Unlike other supernovae that scatter only small amounts of heavy elements, these explosions release enormous quantities of oxygen, carbon, silicon, and even iron. These ingredients drift into space, where they can become part of new stars, new planets, and eventually even life itself. Astronomers believe these explosions were far more common in the young universe. The very first stars, called population 3 stars, were thought to be much more massive than those we see today, and poor in heavy elements. With no metals to cool the stellar gas, these stars grew to extreme sizes, and some likely met their end in pair instability supernovae. Their remains seeded the first galaxies with raw materials for future generations of stars. We may still be seeing the afterglow of those ancient deaths. The James Webb Space Telescope, with its ability to peer over 13 billion light-years into the past, is hunting for the fingerprints of such explosions in the earliest galaxies. Even in our own cosmic neighbourhood, astronomers have identified possible modern examples. One is the unusually bright explosion SN 2007 Bi, which lit up a distant dwarf galaxy. Its light lasted longer than normal, and its spectrum revealed large amounts of nickel, hinting that a gigantic star had blown itself to pieces with no remnant left behind. Another possible case is the superluminous SN 2213Z 1745, whose dazzling light travelled billions of years to reach us. It shone brighter and longer than most supernovae, making scientists suspect a similar pair instability origin. These mysteries are still unfolding. With each new observation and every refined computer model, astronomers move closer to confirming which explosions are true pair instability events. They are more than spectacular fireworks. They are keys to understanding the chemical evolution of the universe. Every time one of these titanic stars dies, it plants the seeds for new worlds and new life. Some of the heavy elements found in the oldest stars of our galaxy may be the ancient fingerprints of such explosions written across time billions of years ago. In the great ocean of the cosmos, many stars are not alone. Instead of drifting through space as solitary travellers, they live in pairs, locked together by gravity. These pairs are called binary systems, and they are surprisingly common throughout our galaxy. Sometimes both stars in a binary system are almost equal, like twin suns circling one another. Other times the partnership is lopsided. One star might be far larger, hotter, or older than its companion. But in some cases, no matter their differences, the two stars slowly creep closer and closer over time. Their orbits shrink, their movements quicken, and eventually the invisible thread that holds them apart snaps. The stars slam together in a furious, fiery embrace. This is the awe-inspiring event known as a stellar merger. Unlike a sudden explosion, a merger begins as a long, patient process. It can take millions, or even billions of years for two stars to spiral together. Stars, like all objects with mass, slowly lose energy. That energy can vanish in the form of gravitational waves, tiny ripples that shake the very fabric of space, or through the interaction of their outer gas layers if the stars are close enough to touch atmospheres. As this energy slips away, their orbits tighten like a whirlpool drawing them inward. If nothing interrupts this dance, no premature explosion, no violent separation, then collision is unavoidable. When stars finally meet, their outer shells of gas and plasma begin to mix. Gravity stretches them, distorts them, and tears at their atmospheres until the boundary between them dissolves. What was once two is now one. A new, larger, and often unstable star is born. The fate of this newborn depends on what kind of stars merged. If both are still burning hydrogen in their cores and are similar in mass, the result can be a bigger, hotter star that shines more brightly than either of its parents. This reborn star may not live long, it burns through its fuel more quickly, but it glows with a strange youthful light. Astronomers call these rejuvenated stars blue stragglers, because they look far too young for the ancient star clusters in which they are often found. What looks like eternal youth is really the scar of a violent union. But not all mergers are so clean. If one star is old and swollen into a red giant, or if one is far more massive than the other, the process can turn messy. The larger star may swell so much that it swallows its smaller companion whole. Their cores may continue orbiting each other deep inside a single bloated envelope of gas. Astronomers call this turbulent stage the common envelope phase. It is one of the most unstable and mysterious periods in stellar evolution. Friction inside this shared envelope can heat the system until the gas puffs outward, sometimes even blowing away into space. What remains might be a pair of exposed cores spinning closely together, or If the merger finishes, one completely new star. Occasionally, the energy of this event bursts outward as a luminous red nova. These eruptions are not as powerful as supernova, but they are still bright enough to be seen across the galaxy. In the year 2008, astronomers watched such an outburst in the Andromeda galaxy. A star brightened for weeks before fading, leaving signs that pointed to a merger rather than a normal supernova. Cooler light, slower debris, and a gentler curve of fading brightness. That same year, another dramatic example unfolded in our own Milky Way. A system called V139 Scorpii had long been a contact binary, two stars so close that they shared a single outer atmosphere. In 2008, they finally collided. The sudden flare of light was the moment of union, giving scientists a rare, direct glimpse of a stellar marriage in real time. When the colliding stars are giants, the spectacle is even more extreme. Their union can trigger fresh layers of fusion, unleashing bursts of light, strange chemical patterns, and new rounds of activity inside the merged star. Such massive stars may burn themselves out quickly and end their brief, brilliant lives in supernova explosions much sooner than they would have otherwise. Some mergers leave behind exotic remnants, ultramagnetic neutron stars known as magnetars, rapidly spinning pulsars, or in rare cases conditions that spark a gamma-ray burst. Though gamma-ray bursts are usually linked to merging neutron stars, evidence suggests that some long-lasting bursts may come from the collapse of ultramassive stars formed in mergers. When such an enormous star spins so quickly that it tears itself apart, it can send out beams of high-energy radiation across the universe. If one of those beams happens to be aimed at Earth, we witness it as a brief but blinding burst of gamma rays. In dense star clusters, where thousands or even millions of stars are crammed into a relatively small region, these events are more likely. Stars tug at each other with gravity, and sometimes they are nudged into deadly embraces. Many of the most massive stars we see today may actually be the products of earlier mergers. Even our own galaxy holds the promise of future collisions. Billions of years from now, the Milky Way will collide with the Andromeda galaxy. The chances of two individual stars smashing directly into one another are slim, since the gulfs of space between them are so vast. Yet, the gravitational chaos of two galaxies merging will stir countless systems. Orbits will twist, binaries will destabilize, and some stars, drawn too close to their companions, will spiral inward and merge. The universe is patient, and in its patience it crafts some of the most spectacular and violent unions imaginable. When a massive star reaches the end of its life and explodes as a supernova, it sometimes leaves behind a strange and compact remnant. This remnant is called a neutron star. At first glance it seems small and almost insignificant, but in truth, it is one of the most extreme objects in the universe. A typical neutron star measures no more than about 20 kilometers across, roughly the size of a large city. Yet within that small sphere is packed more mass than our entire sun. Imagine squeezing the weight of a star 1,000,000 times heavier than the Earth into the size of a city. That is what a neutron star really is. Because of this extreme compression, its gravity is beyond anything our world can even begin to compare with. If you were somehow able to stand on the surface of a neutron star, you would not just feel heavy, you would be crushed instantly. The pull of gravity there is billions of times stronger than what we feel on Earth. Your body, your cells, even your very atoms would be ripped apart in less than a blink. The secret behind this terrifying strength is density. On Earth, we talk about density when comparing how heavy things are for their size, like how a rock is denser than a sponge, or how water is denser than air. But a neutron star takes density to a level so extreme that atoms themselves cannot survive in their normal form. Under such crushing pressure, electrons and protons inside atoms are forced to merge together, creating neutrons. Those neutrons are then pressed so tightly side by side that there is hardly any space left between them. To grasp just how dense this is, a single teaspoon of neutron star matter would weigh about 10 million tons. That is more than the combined weight of every building in a huge city. The surface of a neutron star is believed to be covered by a thin outer crust, only a few hundred meters thick. This crust is made of atoms stretched into rigid chains by the star's gravity. Beneath that crust, things grow stranger still. As you move deeper inside, pressure increases to unimaginable levels. Neutrons, which normally behave like solid particles, begin to flow like a bizarre, ghostly fluid that scientists cannot fully predict. At even greater depths, the pressure becomes so overwhelming that it actually warps space and time. Near a neutron star, clocks tick more slowly, just as Albert Einstein's theory of relativity predicted. Light itself bends as it escapes the surface, curving around the star's gravity so sharply that an observer from far away can see more than half the star's surface at once. It is like looking at a ball from the front but also being able to glimpse part of its back at the same time. Neutron stars are not just dense, they're also fast. Many of them spin at incredible speeds, some turning several times in a single second, and others spinning hundreds of times per second. These fast-spinning neutron stars are called pulsars. As they rotate, they shoot out beams of radio waves or X-rays that sweep across space like the beam of a cosmic lighthouse. When one of those beams passes Earth, we see it as a pulse, so regular and precise that some pulses keep time more accurately than the best atomic clocks made by humans. Scientists even use them as cosmic timekeepers in experiments. The intense gravity of neutron stars also makes them dangerous cosmic traps. If you dropped something as small as a pebble onto the surface, it would smash into it at nearly half the speed of light, releasing an explosion of heat and radiation. Even a grain of sand falling onto a neutron star would produce more energy than a powerful bomb on Earth. This is why neutron stars in binary systems, where they steal material from a companion star, can shine so brightly. The falling matter unleashes immense energy as it crashes onto the surface. Deep at the very center, things may grow even stranger. Scientists do not yet know for sure what lies inside. Some theories suggest that neutrons themselves break apart into even smaller particles called quarks, forming a bizarre state of matter. Others propose that exotic particles like hyperons might appear. These ideas are difficult to test because no laboratory on Earth can create the same crushing conditions that exist inside a neutron star. What we do understand is that the incredible force holding up a neutron star comes from something called neutron degeneracy pressure. This is a quantum effect, a strange rule of physics that says no two identical particles like neutrons can occupy the same exact state at the same time. As the neutrons are squeezed closer and closer together, they push back, resisting further compression. This resistance is what prevents the neutron star from collapsing entirely into a black hole. However, this protection only works up to a limit. If a neutron star becomes too massive, about 2 or 3 times the mass of the Sun, even quantum rules cannot save it. Gravity then wins completely, and the neutron star collapses into a black hole. In this way, neutron stars and black holes are intimately connected, one often being the last stage before the other. As if this were not enough, neutron stars also have magnetic fields of unimaginable strength. In some cases, their magnetic fields are trillions of times stronger than Earth's. Such stars are called magnetars. Their magnetic energy is so fierce that it can snap and twist, releasing titanic flares of radiation. One such flare, if it happened to erupt only a few light years from Earth, could damage our atmosphere. Thankfully, no magnetars that close are known. Occasionally, neutron stars do more than just spin alone in silence. Sometimes they orbit a partner star, or even merge with another neutron star. When they collide, they send ripples through the very fabric of space itself, gravitational waves, which we can now detect on Earth with special instruments. These rare cosmic crashes give us precious glimpses into the hidden physics of these mysterious objects. Most of the time, however, neutron stars remain quiet, almost invisible. They sit as dark, dense reminders of the violent explosions that once ended the lives of massive stars. Tiny giants of crushing gravity, keeping the secrets of matter under pressure that no earthly machine can ever recreate. For many decades, astronomers believed that the densest form of matter in the universe was found inside neutron stars. In this view, once a star collapsed into a neutron star, the only possible next step, if it grew heavier, was to shrink into a black hole. But a bold idea known as the quarknova hypothesis asks a daring question. What if that is not the whole story? Imagine a neutron star sitting at the edge of stability. Its interior is already unimaginably dense, but what if the pressure inside keeps rising? Perhaps the star pulls in more material from a companion, or maybe the conditions inside shift just slightly, pushing it past a hidden threshold. At that moment, according to the theory, something dramatic could happen. The neutrons themselves might shatter. Under this enormous pressure, neutrons could dissolve, releasing the smaller building blocks inside them, quarks. These quarks, usually trapped inside protons and neutrons, would flow freely, forming a strange new state of matter called quark matter. Unlike anything familiar, this substance is not made of ordinary atomic particles. Instead, it is a swirling soup of raw quarks, up quarks, down quarks, and perhaps even the mysterious strange quarks. The change from neutron matter to quark matter would not be smooth or quiet. It would be violent, sudden, and explosive. The neutron star's core would collapse inward, then rebound outward, much like a rubber ball squeezed too hard and snapping back. This rebound could ignite a second explosion, a quarknova. This new blast would come after the original supernova that formed the neutron star. It might erupt hours later, or even days later, unleashing another wave of energy and particles. The two explosions together could explain some of the puzzling supernova-like curves seen by astronomers. Sometimes, instead of fading away smoothly, a supernova brightens again for a short time. In other cases, its light shows unusually strong or strange spectral lines. These odd behaviours might be signs of two blasts. First the supernova, then the quarknova, with the second explosion slamming into the cloud of gas and dust from the first. Some models suggest that quarknovae could release blazing jets of fast-moving particles or even unleash powerful gamma-ray bursts. They might even be behind the most luminous supernovae ever recorded, events that shine 10 or even 100 times brighter than ordinary stellar explosions. Supernovae are already factories of heavy elements, creating things like gold, uranium, and other precious atoms that cannot form inside normal stars. But a neutron star is even richer in neutrons, and under those conditions, even stranger and heavier elements might form. A quarknova, mixing and hurling this material into space, could scatter rare atomic fingerprints that later end up in ancient stars or in the raw material of newborn solar systems. There is another fascinating twist. Some scientists believe that strange quark matter containing strange quarks, might be more stable than ordinary neutron matter. If that is true, then once a small amount of strange quark matter appears, it could spread like a spark catching dry grass, converting nearby neutrons into more quark matter. This chain reaction could transform the entire core of the neutron star into a new type of object, a quark star. Quark stars remain purely hypothetical. No telescope has yet found one, but if they exist, they would be even smaller, denser, and more exotic than neutron stars. They might spin at different speeds, glow with unusual light, or emit strange signals unlike anything else in the cosmos. Even more astonishing, a quarknova could hurl tiny fragments of quark matter into space. These fragments, sometimes called strangelets, would be ultra-dense nuggets, no larger than dust grains but with the mass of mountains. If one ever drifted through our solar system, it might leave behind a faint but detectable trace. The challenge is that quark matter itself is still a mystery. On Earth, scientists have only glimpsed it for the briefest moments inside high-energy particle accelerators, where atomic nuclei collide at nearly the speed of light. Even then, it exists only for a fraction of a second before vanishing. To study it inside stars, astronomers must rely on light and signals travelling from millions of light-years away. Yet, despite these challenges, the quarknova idea opens a thrilling new window into the life and death of stars. If quarknovae are real, they would rank among the most powerful and exotic events in the universe. They would reveal that even after a star has already exploded, its heart may still hide one final act, a hidden explosion deep within, where the smallest building blocks of matter break free and unleash one last cosmic storm. In the still and quiet corners of the universe, pairs of neutron stars drift together in a slow cosmic dance. These stars, the dense remains of once great suns, can circle each other not just for millions but even for billions of years. From a distance, their orbits look calm and steady, like two sparks chasing each other in the dark. But what the eye cannot see is the invisible pull of gravity slowly tightening its grip, drawing them closer together with each passing moment. As time flows on, their orbits shrink, their speed increases, and then, one day, without warning, the stars rush toward one another and collide. The result is one of the most astonishing and powerful explosions the universe can produce, a kilonova. Kilonovas are rare, far less common than the better-known supernovas, but when they happen, they shake the very fabric of space itself. As the stars spiral inward, they send ripples across the cosmos, gravitational waves, waves that stretch and squeeze space as they travel. These waves carry away energy, robbing the system of its balance, until the stars have no choice but to meet in a final, violent embrace. When the collision happens, the neutron stars tear themselves apart. Vast amounts of matter, unlike any ordinary gas or dust, are hurled into space at incredible speeds. This material is special. It is rich in neutrons, far more than any normal element found on Earth. In the glowing outer layers of the blast, the heat and pressure become so extreme that free neutrons begin slamming into atomic nuclei. This process, known as rapid neutron capture, or the R process, builds new elements step by step. Starting from smaller elements such as iron, neutrons are added one by one, and some later change into protons, creating entirely new atoms. And in just a few seconds, nature forges treasures: gold, platinum, uranium, and other heavy elements. These cannot be made inside ordinary stars. They are too heavy and require conditions so extreme that only cataclysms like kilonovas can give birth to them. Without these rare explosions, many of the most precious materials on Earth, like the gold in wedding rings or the platinum in electronics, might not exist at all. The light of a kilonova is unlike the light of a supernova. It rises quickly, usually within a single day or two, then fades over the span of a week. Its colours shift in a strange way, from hot blue to deep red, as the newly formed elements cool and thicken. At first, the explosion shines brilliantly, but as the heavier elements are born, the matter grows opaque, blocking and dimming the light. In the year 2017, astronomers caught their first confirmed glimpse of such an event. Two neutron stars collided in a galaxy about 130 million light-years away. It was historic. Not only did scientists detect the gravitational waves from the crash, but telescopes around the world also captured its visible light. First came the faint ripples in space, then the glow of the kilonova itself, a brief flash from a distant galaxy. In that moment, dozens of Earth's masses worth of heavy elements were created. Some estimates suggest a single kilonova can produce enough gold to fill Earth's oceans many times over. Though they are rare, they do not need to happen often. Just a handful of kilonovas scattered across time can seed entire regions of space with the raw materials for planets, moons, and life itself. Much of the gold in our solar system likely came from kilonovas that erupted long before Earth was born, their riches drifting across space, settling into clouds of gas and dust, and eventually becoming part of the planets. The aftermath of such collisions is equally dramatic. Sometimes, the two stars collapse immediately into a black hole. Other times, they briefly form a massive unstable neutron star that survives for a short while before collapsing as well. During this time, powerful magnetic fields and rapid spins can drive narrow jets of material shooting into space at nearly the speed of light. These jets produce short bursts of gamma rays, flashes so intense that, even though they last only a few seconds, they release more energy than our Sun will ever generate over its entire lifetime. With the help of detectors like LIGO and Virgo, scientists can now catch these events in real time. The detectors pick up the faint tremors of gravitational waves, alerting telescopes to turn toward the sky. Each new discovery adds another piece to the puzzle, helping us understand how elements are forged and how these explosions unfold. Yet mysteries remain. How common are kilonovas truly? Do they always produce the same blend of elements, or do they vary? What becomes of the shattered remnants left behind? These questions keep astronomers searching. Even if we never witness one up close, their fingerprints are all around us. The gold on a ring, the uranium buried in rocks, the platinum inside circuits, all of it born in the fiery death dance of neutron stars colliding in the dark, long before humans walked the Earth. In the entire universe, there are only a few objects as extreme and fearsome as a magnetar. These stars are not just ordinary neutron stars, they are neutron stars taken to the very limit of what nature can produce. Their magnetic fields are the strongest known anywhere in the cosmos, beyond anything the human mind can truly imagine. To put it into perspective, a single magnetar has a magnetic field that is about 1,000 times stronger than that of a normal neutron star. Compared to Earth, its field is almost 1 quadrillion times stronger. That is a 1 followed by 15 zeros. Such a field is not only powerful enough to affect its surroundings in space, it can actually change the structure of matter itself. Atoms near a magnetar do not behave normally. Electrons are forced into narrow, straight paths. Light itself becomes distorted, scattering in strange directions or changing its polarization, and even the vacuum of space, the empty nothing, begins to act like glass or a lens, bending and twisting light in ways that cannot happen anywhere else. Most of the time, magnetars appear quiet and still. They rotate much more slowly than their neutron star cousins, sometimes making just 1 full spin every few seconds. They release only a faint drizzle of X-rays and gamma rays, barely enough to be picked up by the sensitive telescopes orbiting Earth. But this calmness is deceptive. Without warning, a magnetar can unleash a giant flare, one of the most violent outbursts in the known universe. These flares are not powered by nuclear fusion, nor by the crushing weight of gravity, but by the unimaginable stress of the magnetic field itself. Over time, the field twists, bends, and strains against the magnetar's crust. Eventually, the solid crust can no longer hold the pressure. Just as Earth's crust can crack and shift during a powerful earthquake, the surface of a magnetar can suddenly snap. When that happens, all of the energy wound up inside its magnetic field is released in an instant. In less than a single second, a magnetar can release more energy than our Sun produces in 100,000 years. The explosion floods space with X-rays and gamma rays, sometimes rearranging the magnetic field lines of the star itself. These blasts are so powerful that, even from tens of thousands of light years away, they can still be detected here on Earth. One of the most famous of these events happened on December 27, 2004. The magnetar, known as SGR 1806-20, sits roughly 50,000 light years away from us. On that day, its giant flare was so strong that it temporarily reshaped Earth's ionosphere, the thin layer of charged particles high in our atmosphere. Satellites designed to detect nuclear explosions were fooled into thinking a weapon had gone off. Detectors were overwhelmed, even though the flare lasted less than the blink of an eye. If the magnetar had been only a few dozen light years away instead of 50,000, the consequences for Earth's atmosphere could have been devastating. Thankfully, flares of this size are rare. Since astronomers first began watching the skies with modern instruments, only a handful of giant magnetar flares have ever been recorded. More often, magnetars produce smaller bursts, still incredibly powerful compared to almost anything else in the cosmos, but less catastrophic. These bursts are more common when the magnetar is young, while its magnetic field is still restless and evolving. Even the smaller ones can rival the total output of our Sun, but they usually last only moments. Scientists study magnetars not only for their destructive beauty, but because they push the very boundaries of physics. Their fields challenge the limits of quantum mechanics and Einstein's theory of relativity. No experiment on Earth could ever recreate the crushing gravity, the immense pressures, or the magnetic violence of a magnetar. They are nature's own laboratories of extremes. Some researchers even think magnetars may be linked to one of astronomy's most puzzling mysteries: fast radio bursts. These are ultra-powerful flashes of radio waves that last only milliseconds. Some repeat, while others happen just once and never again. In the year 2020, astronomers caught a magnetar inside our own galaxy releasing a burst of radio waves at the very same time it emitted X-rays. Though the signal was weaker than fast radio bursts coming from distant galaxies, it gave scientists their first strong clue that magnetars may be responsible for at least some of these enigmatic events. Yet magnetars do not live forever. Their magnetic fields gradually decay, becoming weaker with each passing century. Within only a few thousand years, a once active magnetar grows quiet, fading into an ordinary neutron star, still spinning but no longer flaring. This makes them rare and difficult to spot. Today, astronomers know of only a few dozen magnetar candidates scattered across the Milky Way. They are discovered by sudden high-energy flashes that vanish almost as quickly as they appear. To catch these elusive giants, satellites such as NASA's Swift and Fermi missions constantly scan the heavens for bursts of radiation. When something triggers an alert, telescopes around the world race to aim at the sky, hoping to glimpse the fading afterglow. Sometimes they find nothing. Other times, the culprit is revealed to be a magnetar. And still, many mysteries remain. Scientists do not fully understand how magnetars are born, or why only certain neutron stars develop such monstrous magnetic fields. Perhaps they are created from especially massive stars that spin quickly before collapsing. Or maybe the chaos following a supernova, the falling back of material, or the presence of a companion star helps twist their fields into existence. Whatever the cause, once a magnetar is formed, it becomes a cosmic time bomb, storing unimaginable energy inside itself, waiting for the moment when its crust will break and the universe will tremble at its roar. In the vast silence of the universe, there exist strange and powerful flashes of energy called fast radio bursts, or FRBs for short. These are not gentle signals, nor are they the steady hums of ordinary stars. Instead, they are sudden bursts of radio waves that last for only a tiny fraction of a second, mere milliseconds, yet they shine with a power that defies imagination. The very first fast radio burst was discovered in the year 2007. Astronomers had been studying old data from the Parkes radio telescope in Australia when they stumbled upon something utterly unexpected. Hidden in the records was a signal unlike anything they had seen before. It was sharp, bright, and came from deep space. At first glance it looked like a glitch, but it was too clean and too strong to be dismissed. This was no random noise. It was a sudden cosmic shout that lasted less than the blink of an eye. Over the following years, nearly an entire decade, more of these mysterious bursts were found. Each one carried its own peculiar traits, and together they became one of the greatest puzzles in modern astronomy. What baffled scientists the most was their strange combination of brevity and raw power. Unlike pulsars or quasars, which beam signals in steady and predictable rhythms, FRBs appeared without warning, like cosmic lightning bolts that flashed once and then were gone. The power behind them is staggering. In a single millisecond, one FRB can release as much energy as our sun does in an entire day. And yet, when astronomers point their most powerful telescopes to the regions of sky where these bursts come from, they see nothing at all. No glowing star, no black hole, no supernova remnant, only invisible fleeting radio waves. At first, many suspected that FRBs were simply the result of technical errors in the instruments, but as more and more were detected by different telescopes around the world, the idea of a mere glitch was abandoned. These signals were real, and they were travelling to us from far beyond our solar system, across the immense ocean of space. Naturally, theories began to bloom. Some scientists believe that fast radio bursts may come from neutron stars or magnetars. Magnetars, with their unimaginably strong magnetic fields, are known to produce violent flares when those fields snap and rearrange themselves. It is possible that FRBs are the grander, more explosive cousins of such events. Others propose that black holes could be involved. Perhaps FRBs are triggered when two black holes collide, or when a black hole devours a neutron star. The immense gravity in such encounters could unleash vast quantities of energy, some of which might escape as a blinding burst of radio waves. Still, no one has found solid proof linking black holes directly to FRBs, so this idea remains a tantalizing possibility. And then there are the more exotic suggestions, the ones that fire the imagination. Could FRBs be the work of alien civilizations, perhaps powerful signals sent across the cosmos by advanced technology? Most scientists treat this idea with caution, but the sheer strangeness of FRBs makes it difficult to rule out completely. For now, however, there is no concrete evidence that these signals are artificial. One of the most fascinating discoveries about FRBs is that some of them repeat. While most bursts are single, one-time flashes, a few have been caught bursting again and again, though at unpredictable intervals. This is unusual because most other cosmic explosions, like supernovae, happen only once. These repeating FRBs suggest that their sources are not destroyed in the process, but instead are capable of firing off bursts over time. This points once more to active cosmic engines like magnetars or neutron stars, possibly in binary systems where magnetic fields and stellar activity collide in spectacular ways. What makes them even more astonishing is their origin. Every FRB observed so far has come from outside our Milky Way galaxy. That means they must be travelling to us from galaxies billions of light years away. The fact that something so distant can still appear so powerful is one of the greatest mysteries of modern astrophysics. Even more intriguing is how these signals are shaped by their long journey. As FRBs cross the space between galaxies, they pass through clouds of electrons and plasma. This causes their waves to stretch, scatter, and slow slightly depending on their frequency. By studying these tiny delays, astronomers are not only learning about the bursts themselves, but also about the hidden structure of the universe, the thin, ghostly material that fills the cosmic void between galaxies. Today, massive observatories and cutting-edge telescopes, such as the Canadian Hydrogen Intensity Mapping Experiment and the once great Arecibo Observatory, are constantly scanning the skies in search of these fleeting signals. Each detection brings us closer to understanding their nature, yet also reminds us how much remains unknown. Fast radio bursts are whispers of cosmic power, blinding shouts from across the universe that vanish almost as soon as they arrive. They are proof that the universe still holds secrets capable of astonishing us, signals that remind us how much more there is to discover among the stars. In the days just before Halloween of the year 2020, NASA decided to put together something fittingly eerie. They compiled a list of the most frightening and inhospitable worlds ever found beyond our solar system. Among these sinister cosmic destinations were 6 exoplanets, each one with conditions so extreme that no living creature could survive even for a moment. In fact, simply drifting too close to some of them might be enough to guarantee certain death. The first of these worlds is a monstrous black gas giant known as TRES 2b. This strange planet circles around a yellow dwarf star called TRES 2, which lies about 718 light-years away from us. From the very beginning, TRES 2b puzzled scientists. Its surface chemistry makes it unlike any other known planet. For reasons still not fully understood, it absorbs more than 99% of all the light that strikes it. In other words, it reflects almost nothing at all, making it darker than coal, darker even than black paint. Astronomers believe there must be some unusual chemical reactions taking place in its atmosphere, reactions never before seen on any other world. Because of this, TRES 2b is considered the darkest exoplanet known in the cosmos. This gloomy gas giant was first discovered on the 21st of August in the year 2006. Over the years, astronomers learned more about it. Its mass is about 1.2 times that of Jupiter, and its radius is roughly 1.27 times larger. The planet's atmosphere is unimaginably hot, around 1000 degrees Celsius, making it glow with a faint red light, like burning embers in a dying fire. Still, despite its terrifying appearance, TRES 2b is not the most dangerous place in the universe. There are far worse nightmares lurking in space. One such world is 55 Cancri e, a planet orbiting a star very much like our Sun, known as 55 Cancri a. This exoplanet was discovered on the 30th of August in the year 2004, using a technique called Doppler spectroscopy. The planet is often called a super-Earth, because it is larger than our own planet but still rocky. Its mass is about 8 times greater than Earth's, and its radius is nearly 1.88 times bigger. What makes 55 Cancri so terrifying is its environment. The planet is tidally locked, meaning one side always faces its star while the other is forever in darkness. The day side is blasted by heat, reaching temperatures as high as 2,400 degrees Celsius. Even the night side is still blistering hot, at around 1,300 degrees. These extreme temperatures come from the planet's close orbit. It lies only about 0.183 astronomical units from its star, which is less than 1/5 the distance between Earth and the Sun. Scientists also believe that 55 Cancri may have volcanic activity. Giant eruptions could spew dust and gas into the atmosphere, forming thick clouds that trap even more heat and prevent it from escaping into space. The planet races around its star in less than 18 hours, completing a year in less time than it takes Earth to complete a single day. Its atmosphere contains helium, hydrogen, and carbon. Deep inside, scientists think carbon may form thick layers of graphite and dazzling diamonds, making this world a glittering but deadly jewel. The 55 Cancri system contains 4 other planets, but none are as hostile as this one. The next planet on NASA's list is far stranger. This is PSR B1257+12c, better known by its ghostly nickname Poltergeist. Unlike most planets, Poltergeist orbits not an ordinary star but a pulsar, the collapsed spinning remnant of a massive star that exploded in a supernova. Poltergeist lies only about 0.36 astronomical units from its pulsar, meaning it is dangerously close to a stellar corpse that beams out deadly radiation. This alone makes it one of the most bizarre and inhospitable planets ever discovered. The system is located about 2,300 light-years away from Earth. Poltergeist itself has a mass about 4 times greater than our planet and circles its pulsar once every 66 days. But the story of its birth is still debated. Some scientists think the planet formed from the debris left behind after the supernova explosion. Others believe it may have appeared after 2 white dwarfs merged together, creating the pulsar without the usual catastrophic blast. Whatever its origin, the intense radiation from the pulsar would shred any spaceship that dared to get near. And yet, even Poltergeist is not the most hellish place out there. If one wishes to see true terror, one must look at Kepler-70b, a world so hot that it might once have been part of its parent star. Kepler-70b is the hottest exoplanet known to us. It orbits a subdwarf star named Kepler-70, whose surface burns hotter than our own Sun at around 6,800 degrees Celsius. The planet itself is tiny compared to Earth, with less than half Earth's mass and about 3/4 of its radius, but it circles its star at a breakneck pace, completing one orbit in just 345 minutes, which means a full year there lasts less than 6 hours. Temperatures on Kepler-70b are beyond imagination. Any matter that dared to come close would be instantly vaporized. What makes this system even stranger is that Kepler-70b regularly passes another planet, Kepler-70c, at a distance of only about 240,000 kilometers, closer than the Moon is to Earth. Nowhere else in space have 2 planets been observed passing each other at such a perilously close distance. Scientists suspect that Kepler-70b's extreme conditions may be because it was once part of its host star before being torn free. But whether it should truly be called a planet is still an open question, one that astronomers continue to study with fascination and dread. It is worth pointing out that the strange world called Kepler-70b is not the only planet known to orbit its star at a dangerously close distance. Another extreme example is the exoplanet WASP-12b, a giant planet that lies about 870 light-years away from our solar system. This world is enormous. Its radius is almost 2 times larger than Jupiter's, measuring precisely 1.93 times Jupiter's size, while its mass is about 1.5 times greater than Jupiter's, or more exactly 1.46 Jupiter masses. But the most frightening detail is how close it is to its star. WASP-12. B orbits at only 3/100ths of an astronomical unit, which means it sits so near its star that its surface reaches scorching temperatures of up to 2,200 degrees Celsius. The gravity of the parent star is so powerful that it is slowly pulling the planet apart, steadily draining material from it. In the grand scale of cosmic time, this destruction will happen rather quickly. Within about 10 million years, WASP-12b is expected to be completely consumed by its star. Because of this grim fate, astronomers know they will likely never learn much more about this doomed world. Exploring such unstable planets is not high on the list of priorities, yet these strange bodies can still hide unexpected and valuable secrets. Sometimes a world may look ordinary at first, but closer inspection reveals a far more dangerous nature. Take the exoplanet HD 189733b as an example. From a distance, it may look peaceful and safe, even resembling Earth with its striking colour, but appearances are deceptive. If one could descend into its atmosphere, they would find themselves in the middle of a stormy nightmare. Winds on this planet reach terrifying speeds of about 8,700 kilometers per hour, fast enough to hurl particles of rock through the air. And as if that were not enough, the planet is lashed by deadly rains of molten glass, which fall sideways due to the violent winds. The cause of such monstrous weather lies in the planet's unusual atmosphere and extremely high temperatures. HD 189733b takes only 2.5 Earth days to complete one orbit around its star, and it is almost certainly tidally locked, meaning that one side is always facing the star while the other remains in darkness. This gas giant is a vivid blue in colour and circles an orange dwarf star in the constellation of Vulpecula. It lies just 63 light-years away from Earth, close by in cosmic terms. Its diameter is about 1.1 times that of Jupiter, while its mass is 113% of Jupiter's mass. The distance between the planet and its star is shockingly small, only about 5 million kilometers, which is roughly 30 times closer than Earth is to the Sun. Because of this, the temperature on its day side reaches around 930 degrees Celsius, while even the night side remains blazing hot, never dropping below 425 degrees Celsius. Soon after its discovery, In the year 2007, HD 189733b became the subject of intense study, especially through observations with the Hubble Space Telescope. Data revealed that the planet's atmosphere is thick and hazy. When the planet passes in front of its star as seen from Earth, the atmosphere takes on a reddish glow. This may be caused by clouds made of tiny particles of iron silicates and aluminum oxide. Even more intriguing, Hubble detected water vapor, neutral oxygen, and organic methane in the planet's skies, along with carbon monoxide on its day side. But the most puzzling finding was a strange type of methane that exists in a fluorescent state, glowing in the infrared part of the spectrum. This unusual chemistry hints at unknown processes at work in the atmosphere, processes that scientists still cannot fully explain. This is a perfect example of how studying extreme worlds, no matter how hostile or unwelcoming, can lead to surprising and important discoveries. Such planets remind us that while they may appear to be nothing more than horror worlds, they are also valuable laboratories of nature. And above all, they serve as a powerful reminder of just how fortunate we are to live on Earth, a planet that is not only survivable, but astonishingly well suited to life. Up to this point, we have already explored some of the most terrifying and deadly worlds ever discovered in the vast ocean of space. Some of them burn with unimaginable heat, others orbit dangerously close to stars that pour out lethal radiation, while still others are cursed with strange and unsettling landscapes. Yet, even with all that, our list of cosmic nightmares is far from complete. Now it is time to meet a few more of these horrifying alien worlds. Our journey begins at a distance of about 202 light-years from Earth. There we find the star known as K2141, an orange dwarf. This star is a smaller cousin of our Sun. It has about 7/10 the mass of our star and measures just under 70% of its radius. Because of this, the two stars share very similar proportions, almost like scaled copies of each other. However, the surface of K2141 is cooler than the Sun's, glowing at about 4,600 degrees Kelvin, roughly 1/5 less than our Sun's temperature. Orbiting frighteningly close to this star, at a distance of only 7/1000ths of an astronomical unit, lies the planet K2141b. This is a rocky world, about 5 times heavier than Earth and 1.5 times larger in radius. These numbers alone tell us something important. The surface gravity there must be at least twice as strong as what we feel on our own planet. To make matters even more extreme, scientists believe that its metallic core makes up between 1/5 and 1/2 of the planet's entire mass. Because it lies so close to its star, K2141b races around in its orbit at terrifying speed, completing one full revolution in only about 6.5 hours. The planet is also tidally locked, which means the same side always faces the star. One hemisphere bakes under endless daylight while the other is trapped in eternal night. On the day side, conditions are hellish beyond imagination. The temperature there reaches more than 3,270 degrees Kelvin, or about 3,000 degrees Celsius. That is hot enough not only to melt rocks and metals, but also to boil them away into vapor. Astronomers believe that the entire day side is covered with a vast, restless ocean of lava that never stops boiling. Above it hangs an atmosphere made of exotic vapors, clouds not of water, but of heavy metals and silicate rock turned to steam. In contrast, the night side is a frozen wasteland. Most of its surface is thought to be dozens of times colder than the fiery day side, with average temperatures far below freezing. This extreme difference in temperature between the two hemispheres drives unimaginably fierce winds, reaching speeds of about 1.75 kilometers per second. That is 5 times faster than the speed of sound on Earth. Imagine the entire planet constantly shaking under the roar of winds so violent they could tear mountains apart. But the nightmare does not stop there. When the superheated atmosphere streams across to the cooler night side, the metal vapors condense and fall from the skies as burning rain. This molten rainfall creates rivers of lava that flow across the dark surface, eventually returning to the blazing day side, where they evaporate once more to begin the cycle again. However, this fiery rain does not cover the entire night side. Most of the vapors cool and fall near the border between night and day, leaving the central parts of the dark hemisphere as barren, frozen deserts locked under layers of solid rock. And yet, K2141b is not even the hottest planet we know. For that, we must look further away, some 670 light-years from Earth, to the world known as Kelt 9b. This world is a blazing gas giant that rivals the very stars in temperature. Its dayside surface burns at about 4,600 degrees Kelvin, over 4,300 degrees Celsius. To put this into perspective, many red dwarf stars, which are actual stars, are cooler than this planet's surface. Kelt 9b orbits the star called Kelt 9, a brilliant white-blue sun about 2 6/10 times as massive as ours and more than twice our sun's diameter. Its surface shines with an astonishing heat of about 10,170 Kelvin, which equals nearly 10,000 degrees Celsius. That ferocious radiation explains why the planet is such a scorching world. Kelt 9b lies only about 1/4 of an astronomical unit from its parent star, closer than Mercury is to our own Sun. It completes an orbit in just a day and a half. Compared to Jupiter, the giant of our own solar system, Kelt 9b is nearly 3 times as massive and about twice as large in radius. Scientists think that deep inside the planet's atmosphere, temperatures may climb as high as 11,000 Kelvin. At such extremes, metals like iron and titanium are vaporized into the air, mingling with hydrogen and helium in a searing chemical brew. The planet is so close to its star and so hot that it is slowly losing its very atmosphere. The intense stellar winds strip away its gases, blowing them into space until they form a great ghostly cloud that trails behind the planet. In time, much of this material will likely be swallowed by the hungry star itself. Here we see 2 very different worlds, one a molten rocky hell where fiery rain pours down over a boiling lava ocean, the other a gas giant so hot it glows like a star while its atmosphere is stripped away into space. Astronomers have discovered that some planets are not only warmed by their stars but also slowly destroyed by them. Take the giant world known as Kelt 9b. According to calculations, this planet may lose as much as 68 Earth masses of material every billion years. If given enough time, Kelt 9b could eventually be stripped of its entire atmosphere and left behind as nothing more than a bare planetary core. Yet this dramatic ending may never come to pass, because its parent star will likely reach the final stage of its life cycle long before that happens, swelling up and devouring everything in its vicinity. This is a sobering reminder that stars are not gentle guardians. They can be merciless destroyers, burning away atmospheres, swallowing planets whole, and erasing entire worlds from existence. And indeed, in the universe there are celestial objects that have already endured the full wrath of their stars. One remarkable example lies 4,570 light-years away, in the region of a small star named V391 Pegasi. Today, this star is a white dwarf, meaning it is the leftover core of a once larger star that has burned through all of its fuel. Its mass is about half that of our Sun, and its radius is only about 23% of the Sun's size. Despite being so small, it still burns with an astonishing surface temperature of nearly 30,000 Kelvin. All nuclear reactions inside it ended long ago, and now it faces hundreds of billions of years of slow cooling, until it eventually fades into a cold, dark black dwarf. Orbiting this stellar remnant is a planet known as V391 Pegasi b, and its story is nothing short of astonishing. According to scientific models, this planet not only survived its star's transformation into a red giant, but even passed through the outer layers of the dying star. When V391 Pegasi expanded into a giant, its outer atmosphere was so thin and spread out that it brushed against the planet's orbit. The gas there was dozens of times less dense than the air we breathe on Earth, which meant that any planet swallowed into it would not be destroyed instantly. Instead, it would lose energy and slowly spiral deeper into the hotter, denser layers. But in this case, the star shed its outer layers just in time, shrinking into a white dwarf before V391 Pegasi b could melt away completely. Miraculously, the planet survived. Today, it appears to be a gas giant about 3 times more massive than Jupiter. It orbits its star at a distance of about 1.7 astronomical units, which is roughly the distance between Earth and Mars from the Sun, and it takes around 1,170 Earth days to complete a single orbit. Scientists are still puzzled as to how this planet managed to keep so much of its mass after brushing through the fiery layers of a dying star. Clearly its orbit and characteristics were dramatically altered during that encounter, making it impossible to know what the planet looked like before its plunge into the sea of plasma. The cosmos is filled with such strange and hostile worlds, some so unusual that they almost defy imagination. Many of them cannot be seen with ordinary telescopes because they are faint or hidden, but astronomers can detect them by studying radio waves. This is especially true of planets orbiting pulsars, a type of neutron star that spins at dizzying speeds while beaming out powerful pulses of radiation. One such pulsar lies about 4,000 light-years away from Earth. Despite its enormous mass, it is tiny. Its diameter is only about 20 kilometers, yet it packs in about 1 4/10 times the mass of our Sun. This ultra-dense object spins at a staggering rate of nearly 10,000 rotations every minute, sending out constant blasts of electromagnetic radiation like a cosmic lighthouse. And orbiting this pulsar is another extraordinary planet. Its surface is bombarded by waves of lethal radiation, making it utterly hostile to any form of life. The planet races around its star in just 2 hours, at a distance of only 600,000 kilometers, less than the radius of our Sun itself. This strange world is estimated to have a mass of about 330 times that of Earth, and a radius 4 times larger than our planet's. That means gravity on its surface would be about 20 times stronger than Earth's gravity. Even more astonishing, its density is about 23 grams per cubic centimeter, far denser than most substances we know. Astronomers believe it is composed mostly of crystallized carbon under immense pressure. In other words, it could essentially be a gigantic diamond world. The upper layers also contain oxygen, most likely chemically bound to carbon. It seems unlikely that such a planet could have survived the violent explosion of a supernova, which is what created the pulsar. Instead, scientists think it may have formed afterward, from the remnants of a white dwarf star that was torn apart. This makes classifying the planet very difficult, as it may not fit neatly into the usual categories. Whatever its origins, one thing is certain. This world is among the most extreme and forbidding places in the cosmos. With crushing gravity, lethal radiation, and a body forged from diamond-like carbon, it stands as a reminder of the bizarre and deadly possibilities the universe can create. About 650 light-years away from Earth, there exists a truly majestic and mysterious star known as IRC 10216, more commonly called CW Leonis. This red giant is one of the most fascinating dying stars ever studied. At its peak size during pulsation, CW Leonis swells to an astonishing radius about 560 times greater than that of our Sun. To imagine this, think of placing CW Leonis in the very centre of our solar system. Its bloated atmosphere would stretch so far outward that every planet up to and including Mars would be swallowed beneath its fiery layers. Its edge would even brush against the inner boundary of the asteroid belt, leaving very little of our familiar solar neighbourhood untouched. Yet despite its enormous bulk, the mass of CW Leonis is not especially high. It is thought to be only about 1 1/2 to 4 times that of the Sun. Its surface is also surprisingly cool compared with many other stars, measuring only about 2,300 degrees Kelvin, or around 2,000 degrees Celsius. But what the star lacks in surface heat, it more than makes up for in sheer size. Thanks to its gigantic dimensions, CW Leonis shines with an average brilliance about 8,500 times greater than that of the Sun. Like all red giants, CW Leonis is living through the final chapter of its existence. Astronomers cannot say with certainty how old it is, but they believe it has already survived for several billion years. Long ago, in its youthful days, it was likely a hot white blue star with a mass about 3 to 5 times greater than that of the Sun. Roughly 1 billion years ago, much of its hydrogen fuel was used up and converted into helium. This helium gradually settled into the core of the star, forcing out the remaining hydrogen and forming a dense, scorching hot central region. This region no longer participated in ordinary nuclear reactions. That change marked the beginning of the great transformation into a red giant. The immense pressure inside the star caused its outer layers to expand to an almost unthinkable size. As the atmosphere swelled, it became thinner and more unstable, while the star's glow shifted to a deep blood-red colour. Inside the heart of CW Leonis, however, nuclear reactions did not stop. They continued until the pressure and temperature became so extreme that a dramatic event occurred, the helium flash. During this process, helium nuclei fused into carbon, triggering a sudden and powerful release of energy. The The star's inner structure was reshaped, its core heated to incredible temperatures, while its outer layers cooled and dimmed. Now, CW Leonis is rich in carbon, yet its mass is not large enough to push forward to the next stage of element creation. Instead, the nuclear reactions in its interior are unstable. The star goes through cycles, its interior heats up, nuclear fusion blazes, and the star expands. Then the fusion slows, the outer layers cool, and gravity forces the star to contract once again. After that, the cycle repeats. These cycles are visible from Earth as periodic changes in the brightness of CW Leonis. Its pulsation period lasts about 649 days. At its brightest, the star shines about 11,300 times more powerfully than the Sun. Even at its dimmest, it still radiates about 6,250 times more energy than our star. During these contractions, some of the upper layers of the star's atmosphere are pushed outward and torn away, creating a thick shroud of gas and dust made of carbon and oxygen. This forms a vast nebula that envelops CW Leonis. It is estimated that the star loses roughly 4 times 10 to the power of 22 tons of material each year, which over time adds up to about 7 times the mass of the entire Earth. This circumstellar nebula is thought to be at least 69,000 years old. Its total mass is about 1.5 times that of the Sun, and its diameter stretches an incredible 84,000 astronomical units, far beyond the size of our solar system. The nebula is not a smooth, uniform cloud, but a complicated structure filled with bulges, pockets of gas, arcs, and irregular rings. Astronomers believe that magnetic fields and turbulent stellar winds from the unstable star are what carved out these strange formations. What makes this surrounding cloud even more intriguing is its chemical composition. Spectral studies reveal the presence of about 70 different compounds. Among them are carbon dioxide, water, and ammonia, along with heavier elements from the upper reaches of the periodic table, extending all the way down to iron. It is possible that CW Leonis once hosted planets in its system, but if they existed, they were likely engulfed long ago when the star expanded into its red giant phase. To this day, astronomers have not detected clear evidence of planets orbiting it. The only hints of past companions are faint and subtle variations observed in the star's orbit, as though echoes of a planetary system that once was. Back in the year 1994, and then again more recently in the year 2017, astronomers noticed something strange happening around the star known as CW Leonis. Shifts of matter were seen within the enormous cloud of gas and dust that surrounds it. Some scientists suggested that a tiny red dwarf star, quietly orbiting this bloated giant, might be the cause of these mysterious changes. Yet, despite repeated attempts, no one has ever managed to detect the faint radiation such a companion star should give off. One possible reason is that the nearby nebula, the thick and glowing mist of gas and dust, scatters and reflects surrounding light. This makes any hidden objects within its veil extremely hard to see, almost as if they were cloaked. If such a small companion does indeed exist, it would be lighter than our Sun. Astronomers believe that it would need about 1 full century to circle once around CW Leonis. But there is another even more curious mystery in this star's neighbourhood. The cloud around CW Leonis contains an unusually high amount of water. At first, scientists thought the water came from icy comets, swallowed as the red giant expanded. That idea, however, began to fall apart in the year 2009. During that year, astronomers studying the light from the star discovered spectral lines with temperatures of around 1000 Kelvin. Such heat could only mean that water vapour was actually forming in the upper layers of the giant itself. This was baffling. According to the models of red giant stars that scientists used at the time, all the oxygen near such a star should already be bound into carbon monoxide, leaving none available to form water. To explain this puzzle, a new idea was proposed. Powerful ultraviolet radiation could be breaking apart molecules of silicon oxides and carbon. Once freed, the oxygen atoms could then combine with hydrogen to form scorching hot water vapour. The flaw in this idea, however, was that no clear source for such strong ultraviolet radiation had been found. Normally, stellar matter shields itself very effectively from outside cosmic rays. Yet there may be another explanation. CW Leonis is not a stable star. It trembles, swells, and sometimes tears itself open with great rifts and thin patches on its surface. Through these weak spots, ultraviolet radiation may escape, triggering the chemical reactions that create water. The amount of water vapour in CW Leonis' envelope is almost unimaginable. Astronomers estimate it at several quintillion tons, an amount so vast it is difficult to picture, and yet, compared to the star's total mass, this enormous quantity makes up only about a billionth of it. CW Leonis, like all red giants, is in the twilight of its life. In perhaps 10 to 30,000 years, just the blink of an eye in cosmic time, it will burn through the last of its fuel. At that point it will shed its outer layers in a titanic outburst. What remains will collapse into a white dwarf, a small but unimaginably dense star with a mass about 80% of the Sun's. Its surface will blaze at several million degrees during the first moments after its birth, but without a fresh energy source it will slowly cool. Over billions of years, it will dim further and further until it becomes a black dwarf, nearly invisible in the dark ocean of space. But before this quiet ending, CW Leonis will make one final magnificent contribution to the cosmos. In the violence of its death throes, the shock waves and extreme temperatures at the star's core will forge heavy elements that cannot exist in normal stellar interiors, elements such as uranium, gold, and lead. These newly born atoms will be cast out into space, where, over millions of years, they may become part of newborn stars, planets, and even oceans. Radioactive elements can heat planetary interiors, melt hidden ice, and enrich seas with vital minerals, creating the conditions for life itself to appear. The inside of any star is unimaginably hot, and this is hardly surprising. Such extreme heat is absolutely necessary for the process of thermonuclear fusion, the mighty engine that powers every star in the universe. In these fiery depths, atoms of hydrogen collide and merge, forming helium. Each of these fusions produces not only a helium atom but also an electron, several ghost-like neutrinos, and most importantly a tremendous burst of energy. But hydrogen fusing into helium is not the only reaction that can occur within stars. When the temperature climbs even higher, other elements such as lithium, carbon, or oxygen can take part in nuclear reactions as well. These processes forge heavier elements like sulfur, magnesium, or phosphorus. However, the more massive the element, the greater its electrical charge, and the stronger the repulsion between its atomic nuclei. It takes far more energy to force them to fuse, which is why only the hottest and heaviest stars can carry out such reactions. When a star in the main sequence stage exhausts most of its hydrogen, its fate begins to change. It swells outward, growing cooler and redder, and eventually becomes a red giant. In this stage, the star no longer fuses hydrogen, but instead burns helium, transforming it into carbon and oxygen. Yet the destiny of a star depends on its size. Smaller stars burn out faster, shedding their outer layers when they become unstable, and finally collapsing into a white dwarf. These stellar remnants, with no fuel left for fusion, cool slowly over billions of years, fading into darkness. Massive stars, however, follow a far more dramatic path. If a star's mass is above a critical value, fusion of heavier elements continues long after hydrogen is gone. Such extraordinary stars are known as Wolf-Rayet stars, a rare and fascinating class first identified in the year 1867 by the French astronomers Charles Wolf and Georges Rayet. Their discovery came when the scientists noticed strange and unusually bright emission lines in the star's spectra, lines produced not by hydrogen, but by heavy elements. Wolf-Rayet stars are generally enormous and nearing the end of their lives. They contain little hydrogen but glow with intense power, fueled by the fusion of heavier nuclei. Despite their brilliance, they are extremely rare. Astronomers have found only a few hundred of them in our Milky Way galaxy, and estimates suggest that there cannot be more than about 2,000 in total. These stars are divided into three main groups depending on which element dominates their spectrum: nitrogen, carbon, or oxygen. Each group is then subdivided into smaller types. Among these blazing giants is one of the hottest stars ever studied, WR102. Discovered in the year 1971, it was first mistaken for the visible counterpart of an X-ray source known as GX3+1. Later, detailed spectral analysis revealed that WR102 was a separate object, with astonishingly bright oxygen emission lines. By 1982, WR102 and 4 other stars had been recognized as a new class of Wolf-Rayet stars. The surface temperature of WR102 is breathtaking, over 210,000 Kelvin, making it about 36 times hotter than our Sun. Its luminosity is equally staggering, shining more than 380,000 times brighter than the Sun. And yet, despite this brilliance, it remains invisible to the naked eye, lying some 10,000 light-years away in the direction of the constellation Sagittarius. WR102 belongs to the rare oxygen-rich Wolf-Rayet stars, which contain almost no hydrogen. Instead, they draw their energy from the fusion of heavy atomic cores such as carbon, neon, and oxygen. To date, only 9 such stars are known, 4 in our Milky Way and 5 in other galaxies. 2 reasons explain why these oxygen-sequence Wolf-Rayet stars are so uncommon. First, only very massive stars, those born with at least 40 times the mass of our Sun, can become Wolf-Rayet stars. Second, this stage is incredibly brief in cosmic terms, lasting anywhere from 1,000 to 10,000 years, no more than a fleeting moment on the astronomical timescale. Though WR102 is small compared to many supergiants, it is astonishingly dense. Its radius is only about 58% that of the Sun, yet its mass ranges between 15 and 18 solar masses. At birth, however, it may have been as heavy as 40 to 60 suns. Over time, the star has lost much of its mass through a furious stellar wind, where particles stream outward at speeds exceeding 5,000 kilometers per second. In just a few months, the star sheds material equal to the mass of the Earth, and over 10,000 years it will lose mass comparable to that of the entire Sun. Surrounding WR102 is a shell of gas, sculpted into beautiful arcs and filaments by the star's ultraviolet radiation and intense winds. Some astronomers suggest this gas may be the stripped remains of the star's original hydrogen-rich layers, while others think it is material expelled more recently by the stellar wind. WR102 is not alone in its blistering heat. Other Wolf-Rayet stars such as WR142, WR3A, and WR993b, as well as the central star of the Bug Nebula, reach surface temperatures of around 200,000 Kelvin. Certain white dwarfs also rival these numbers, yet even these pale compared to newborn neutron stars, whose temperatures can reach 100 billion Kelvin at birth, cooling rapidly through floods of neutrinos, but never falling below several 100,000 Kelvin at their surfaces. Still, none of these records compare to the unimaginable temperature at the very birth of the universe. At the instant of the Big Bang, the cosmos is believed to have reached about 1.4 times 10 to the power of 32 Kelvin, a value known as the Planck temperature. Beyond this limit, the laws of physics themselves cease to function in any way we can presently understand. Returning to WR102, we now know it is nearing the final chapter of its life. Unlike ordinary stars, Wolf-Rayet stars do not swell into giants in their last days. Their enormous gravity holds them tightly together in a blazing, compact sphere. But as WR102 continues to lose mass, it will eventually destabilize and explode as a supernova, an event likely to occur sometime within the next 1,500 years. Because it is 10,000 light-years away, it is even possible that the explosion has already happened, though its light has not yet reached us. When this mighty detonation comes, it will unleash powerful gamma-ray bursts and forge new heavy elements, including transuranium ones. What remains of the star will collapse into an ultra-dense neutron star, while its outer layers will be hurled into space, forming a glowing nebula. Over billions of years, this material may someday become the seeds of new stars and planets. It almost goes without saying that finding a celestial object that swallows every single beam of light falling upon it is one of the hardest challenges in astronomy. A black hole gives off no light of its own, and because of that, it is like searching for the darkest shadow in the deepest night. This explains why, even today, the number of confirmed black hole candidates remains relatively small. Still, scientists using mathematics and computer models estimate that the Milky Way galaxy could contain as many as 100 million black holes. That sounds unimaginably large, but when compared with the estimated 200 to 400 billion stars in our galaxy, it shows us that black holes are actually rare wanderers among the star-filled oceans of space. In earlier discussions, we mentioned that only very massive stars can give birth to a black hole. A star must weigh at least 18 to 20 times more than our Sun to end its life with an explosion so powerful, a supernova, that it squeezes its fiery heart into an unimaginably dense lump of matter. Once this happens, nothing, not even light itself, can escape its crushing gravity. The border that defines this point of no return is known as the Schwarzschild radius. Beyond that invisible wall, the star ceases to be what it once was and becomes a strange entity that bends the very laws of physics as we understand them. One of the black holes closest to Earth is called A06-0000, also known as V6-16 Monotorotis. This dark object is found about 3,300 light-years away from us, nestled in the constellation of Monoceros, the unicorn. It belongs to a binary system, meaning it shares its existence with a visible star. Its companion is a small orange dwarf star, with about half the mass of our Sun. Every 7 hours and 45 minutes, this orange dwarf faithfully circles around its invisible partner. Astronomers estimate that the hidden object has a mass roughly 6.5 times greater than our Sun, which is far too heavy to be a neutron star. This leads to the strong conclusion that it must indeed be a black hole. The orange dwarf, caught in the black hole's powerful embrace, is stretched and deformed, and its outer layers are steadily torn away. Streams of blazing hot gas spiral inward, forming a glowing disk of matter known as an accretion disk. It is this fiery, radiant disk that betrayed the black hole's existence, making the invisible visible. Around V6-16 Monocorotis there are dozens of other stars, many of which likely have planets of their own. Someday, one of these neighbouring stars may drift too close to the black hole. If that happens, the monster's gravity will pull it in, sealing the star's fate. It would suffer the same slow destruction now being endured by the orange dwarf companion. The way a black hole interacts with nearby objects depends heavily on the balance of their masses and the distances between them. The more massive the black hole and the closer its companion, the stronger its tidal forces, the same kind of stretching forces that the moon exerts on Earth's oceans, but on a terrifyingly larger scale. These forces can twist a star into elongated shapes, funneling its material into streams that feed the black hole's accretion disk. If the forces are strong enough, the star may not survive at all, being torn apart into a blazing ring of matter before disappearing forever. Interestingly, planets may orbit black holes just as they orbit ordinary stars. Despite their sinister reputation, black holes do not pull everything in around them indiscriminately. Gravitationally, they behave just like any star of the same mass. This means that, in theory, a stable planetary system could exist around a black hole. There are several ways such worlds might come into being. First, new planets could form from a cloud of gas and dust left behind after a supernova explosion. Under the black hole's gravitational influence, clumps of matter would collide and grow, eventually becoming planets, moons, asteroids, and comets. The radiation from the accretion disk might even warm these bodies, melting ice and possibly creating conditions where life could appear and develop. Second, if a black hole destroys a nearby planetary system, not everything would necessarily be lost. Some surviving planets might settle into new, stable orbits around the black hole. Their surfaces would change dramatically. A gas giant might lose most of its hydrogen and transform into a rocky world, or an ice-covered planet might thaw into an ocean world. Third, lonely wanderers, rogue planets or drifting asteroids travelling through interstellar space could be captured by a black hole's gravity, becoming new members of its system. Although no such planetary systems around black holes have yet been confirmed, there is no scientific reason to believe they cannot exist. Of course, if a planet strays too close to the blazing accretion disk, it faces a grim destiny. The scorching radiation and friction would strip away its atmosphere and drag it closer and closer to the black hole. In the end, the immense tidal forces would rip the planet apart, scattering its remains into countless fragments. These fragments would spiral into the accretion disk, heat up, melt, and finally be consumed, becoming one with the black hole itself. Scientists believe that there are 3 main kinds of black holes in the universe, and what sets them apart above all else is their mass. Each type has its own strange story, and a unique way of shaping the cosmos. The first kind are the true giants, the so-called gargantuan black holes that lie at the very hearts of most spiral galaxies. Their masses can reach several billions of times the mass of our Sun. The central regions of galaxies are places where matter is incredibly dense, and because of this, stars form there in enormous numbers, often tightly packed together. These stars burn with extraordinary brightness, but also live very short lives. When they run out of fuel, they collapse and become black holes. Over time, many of these smaller black holes merge and grow, giving birth to monstrous supermassive objects. Around these giants swirl enormous accretion disks made of gas and dust heated to unimaginable temperatures. These disks shine so brilliantly that they can be seen from billions of light years away, even when the galaxy they belong to is too faint to be visible. Such dazzling beacons are called quasars, and they are some of the brightest objects in the entire universe. The second type of black hole is far more common, though much harder to spot. These are black holes with masses similar to those of stars. They are born when very massive stars reach the end of their lives, collapse under their own weight, and die in violent explosions. After their birth, these stellar mass black holes may grow larger by feeding on nearby stars or swallowing interstellar gas. If several of them merge, they may evolve into what astronomers call intermediate mass black holes. When such mergers take place, they produce powerful ripples in the fabric of space itself, what we know as gravitational waves. These waves can travel for many light years, stretching and compressing space as they pass. The third type belongs more to theory than to direct observation. These are the so-called primordial black holes, thought to have formed in the very earliest moments of the universe. According to cosmological models, tiny fluctuations in the dense soup of matter that filled space shortly after the Big Bang may have caused black holes of incredibly small size to appear. The smaller such a primordial black hole is, the faster it is believed to evaporate. At the very end of its life, one of these objects would explode in a final outburst of energy, releasing a tremendously powerful electromagnetic signal. Some calculations suggest that primordial black holes with masses of about 10 to the power of 12 kilograms should be burning out right around our present time. Yet, despite careful searching, astronomers have never observed such an event. There is also another bold idea, that in rare collisions of extremely high-energy particles, a quantum black hole might briefly form. These would be microscopic black holes, existing only for the tiniest fractions of a second. The conditions required for such an event cannot be recreated in laboratories on Earth, and the expected lifetimes of these hypothetical objects are so short that even our most advanced instruments would struggle to detect them. For now, quantum black holes remain purely theoretical. Detecting any kind of black hole is never easy, since by their very nature they swallow all light. Sometimes astronomers notice a star that behaves strangely, moving in a way that suggests an unseen companion is tugging at it. This invisible partner is often a black hole. Another method is to study accretion disks. The glowing gas spiraling around a black hole emits radiation with very specific signatures, which makes it possible to distinguish them from ordinary stars or galaxies. In rare cases, telescopes have even managed to capture images of accretion disks with a dark, round patch at the center, the unmistakable silhouette of a black hole. Black holes can also reveal themselves through a phenomenon known as gravitational microlensing. When a massive but invisible object passes directly between Earth and a distant star, its gravity bends the light from that star. The star's brightness and spectrum change in a very distinctive way, allowing astronomers to infer the hidden presence of a black hole. However, this method works only when a number of rare cosmic alignments occur, which makes such detections especially precious. When a star is born, it begins its life as a giant ball of glowing gas, shining brightly thanks to the power of nuclear fusion. In its core, hydrogen atoms collide and merge together, forming helium and releasing enormous amounts of energy. This energy creates light and heat, and also pushes outward, balancing against the immense pull of gravity that is constantly trying to crush the star inward. For millions, and sometimes even billions of years, this tug-of-war between outward pressure and inward gravity keeps a star stable and shining. But nothing in the universe lasts forever, not even stars, and when the fuel at the heart of a massive star runs out, the story takes a darker and far more dramatic turn. At this moment, the very heart of the star begins to fail. The nuclear reactions that once held gravity at bay come to a halt. The outward pressure disappears almost suddenly, and gravity, which has been waiting patiently all this time, takes control. The core of the star, which has been growing heavier and heavier with time, begins to collapse under its own incredible weight. For stars smaller than a certain size, this collapse leads to a white dwarf or perhaps a neutron star. But for truly giant stars, those many times larger than our Sun, the collapse is so overwhelming that it cannot be stopped, not by any known force in nature. As the collapse begins, matter is squeezed tighter and tighter, packing into a space smaller than ever imagined. The neutrons, which in normal neutron stars provide resistance through a phenomenon called neutron degeneracy pressure, can no longer bear the crushing force. Even these dense particles yield to gravity's relentless pull. The collapse speeds up, unstoppable, like a waterfall plunging downward with terrifying speed. The heart of the star shrinks into an unimaginably small and dense point, and the laws of physics as we currently understand them can no longer describe what is happening. At this moment, a singularity is born. A singularity is the strangest of cosmic creatures. It is a place where matter is compressed into an infinitely small space, where density and gravity become infinite, and where our equations break down completely. The mind can barely grasp it, an object with the mass of an entire star reduced to a point smaller than anything measurable. Around this singularity forms an invisible boundary called the event horizon. This horizon is not a surface in the ordinary sense, but a point of no return. If anything crosses this invisible line, be it light, matter, or even time itself, it is forever trapped, pulled inevitably into the singularity's embrace. Nothing can escape, not even the fastest thing in the universe, light itself. And thus, a black hole has come into existence. Though the black hole itself is hidden, the drama of its birth is not. The death of a massive star is marked by one of the most violent events in the cosmos, a supernova explosion. In the final throes of collapse, shock waves rip through the outer layers of the star, blowing them apart into space. The amount of energy released in such an explosion defies imagination. It can outshine entire galaxies of billions of stars for a brief moment in time. With this explosion, the star scatters heavy elements like iron, gold, and uranium into the surrounding space. These are the elements that will one day form new planets, new stars, and even the building blocks of life itself. In this way, every black hole carries within it not only the death of a star, but also the promise of new beginnings elsewhere in the universe. During the collapse, a vast flood of particles called neutrinos is unleashed. These ghostly particles pass through nearly everything without stopping, but in such numbers they carry away a tremendous amount of energy. Alongside the neutrinos, radiation and kinetic shock waves race outward, reshaping the cosmic environment. These shock waves compress nearby clouds of gas and dust, sometimes sparking the birth of entirely new stars. The cycle of life and death in the universe continues, driven by these magnificent explosions and the black holes they sometimes leave behind. Every time a star heavy enough to collapse into a black hole reaches the end of its life, this same grand story plays out. A star lives, it shines, it exhausts its fuel, and then it collapses. Sometimes it leaves behind a quiet remnant like a white dwarf, or a dense, rapidly spinning neutron star. But in the most extreme cases, the collapse goes beyond these limits, and a black hole is born. Each black hole is, in a sense, the final memory of its star, holding the secrets of its last moments in its invisible depths. The precise way a black hole forms depends on many details: the mass of the star, the mix of elements in its core, the speed of its rotation, and the strength of its magnetic fields. These factors can influence whether the star's final collapse is swift and violent or more gradual, and whether the resulting black hole is relatively small, only a few times the mass of our Sun, or enormous, reaching millions or billions of solar masses. Many black holes are not isolated wanderers but part of binary systems. In such a pairing, the black hole shares its existence with a companion star. The powerful gravity of the black hole can pull gas from its companion, stripping it away and forming a swirling disk of matter called an accretion disk. This disk glows fiercely as the gas spirals inward, heating to incredible temperatures. In its final desperate fall toward the event horizon, the gas shines in X-rays and other high-energy radiation. Though we cannot see the black hole itself, these signals provide astronomers with vital clues. By studying the radiation, scientists can measure the properties of the black hole, such as its mass, its spin, and even the way it bends space and time around it. Sometimes the dance between black holes goes even further. In the vast stretches of the universe, two black holes may find themselves locked in orbit around each other. Slowly, over millions of years, they spiral closer and closer, losing energy in the form of ripples in space-time called gravitational waves. When the two black holes finally collide and merge, They release a titanic outburst of energy in the form of these waves, which race across the cosmos at the speed of light. Billions of years later, tiny detectors on Earth can feel these faint vibrations, like the echo of some distant cosmic thunder. These discoveries confirm what Albert Einstein first predicted in the early 20th century and allow us to witness black hole mergers across unimaginable distances. The birth of a black hole has profound meaning for our understanding of the universe. Near a black hole, gravity is so extreme that the very fabric of space and time is warped. Time itself behaves strangely, slowing down relative to the outside world as one approaches the event horizon. A traveller nearing the horizon would see the universe outside rushing forward, while to outside observers, the traveller would appear frozen at the edge, never quite crossing over. The singularity hidden inside remains the greatest mystery. It is a place where our mathematics fails, where quantum mechanics and general relativity, two of the greatest pillars of physics, no longer agree. To solve the riddle of the singularity is to seek a deeper understanding of reality itself. Black holes, then, are not just the remains of dead stars. They are cosmic laboratories, places where the laws of physics are pushed to their ultimate limits. They remind us of how much we still do not know about the universe and how many secrets remain hidden in the dark. They show us the immense power of gravity and the fragility of even the mightiest stars. At the same time, they connect us to the cycle of creation. The very elements of our bodies, the oxygen we breathe and the iron in our blood, were forged in the furnaces of stars and scattered by supernova explosions. Without the deaths of massive stars and the black holes they sometimes leave behind, life as we know it would not exist. To imagine the story of a single black hole is to imagine a tale stretching across millions of years. First, a giant star is born from a cloud of hydrogen and helium gas, glowing bright in the sky. For countless ages it shines, a beacon of light across the galaxy. Then, at last, its fuel runs out and its heart begins to collapse. The final blaze of glory, the supernova, lights up the heavens, and in the silent darkness that follows, a black hole remains. Invisible, yet immensely powerful, it waits in space, tugging at the stars around it, bending light and whispering secrets of the universe. And this story is not rare. In our own galaxy, there may be hundreds of millions of black holes, each one born from the death of a star. Across the cosmos, scattered in galaxies beyond number, the population of black holes must be staggering. Some are small, only a few times heavier than the Sun. Others, at the centres of galaxies, weigh as much as billions of suns, devouring matter and shaping the very structure of galaxies. The universe itself is filled with these mysterious objects, both terrifying and awe-inspiring. Each black hole is like a scar in space, marking where a star once lived. But these scars are not only reminders of destruction, they are also symbols of transformation. Through the deaths of stars and the birth of black holes, the universe recycles itself, turning death into new life, endings into beginnings. The story of black hole formation is therefore not only about collapse and finality, but also about renewal, rebirth, and the unending cycle of cosmic evolution. Black holes may be invisible, but their presence shapes the destiny of galaxies. Their formation is both an end and a beginning. They are the dark hearts of the cosmos, the silent keepers of secrets that we may never fully uncover. And yet, in trying to understand them, we learn more about ourselves and our place in the universe. Every black hole is a reminder that even in darkness there is wonder, and even in the silence of collapse there is the echo of creation. Black holes, those mysterious and invisible giants of the cosmos, are often imagined as quiet, eternal gluttons, steadily pulling in matter that wanders too close. Yet there are times when they abandon their slow, steady feeding habits and turn into ferocious monsters, gulping down everything within reach with a hunger that seems limitless. This state is known as hyperaccretion, or what one might call a black hole's supercritical feeding frenzy. To understand the sheer drama of this process, one must first picture how a black hole normally eats. A black hole is not a physical object with a surface like a star or a planet. Instead, it is a region of space where gravity is so unimaginably strong that not even light can escape. Around many black holes, especially those in the centres of galaxies or those locked in stellar partnerships, a swirling disk of matter forms. This disk, called an accretion disk, is made of gas, dust, shattered remnants of stars, and sometimes even streams of material pulled from a companion star. Normally, the black hole feeds at a controlled pace, like a predator patiently consuming its meal. Matter spirals inward, heating up from friction and pressure, glowing brightly before finally vanishing past the event horizon, the point of no return. But every so often, the black hole is confronted with a banquet rather than a modest meal. Perhaps a massive gas cloud drifts too close. Perhaps a star ventures near, only to be ripped apart in a tidal disaster. Or perhaps a companion star sheds so much material that the black hole cannot keep up. Suddenly, the inflowing material begins to pile up, and the disk becomes unimaginably dense and turbulent. This is the beginning of hyperaccretion, a period where the black hole feeds thousands of times faster than usual, in an orgy of consumption that transforms it into one of the brightest and most violent objects in the universe. In this state, the accretion disk becomes a cosmic furnace. Temperatures rise not to thousands, not even to hundreds of thousands, but to millions of degrees. Matter swirls inward at speeds approaching the speed of light. The immense friction between layers of gas and plasma releases staggering amounts of energy, so much that the disk shines across the entire electromagnetic spectrum. It emits visible light, but also invisible radiation in the form of X-rays and gamma rays, the most energetic kinds of light known. At its peak, this single glowing disk can outshine an entire galaxy, a galaxy that itself may contain hundreds of billions of stars. The term feeding frenzy is no exaggeration. Imagine an ocean predator suddenly finding itself in the middle of an endless school of fish, snapping and devouring in a blur of violence. The black hole is that predator, except instead of fish, it is devouring stars, gas, and cosmic dust. The gravitational pull drags matter inward faster and faster, accelerating the process in a runaway cycle. The more material falls in, the more energy is released. The more energy is released, the hotter and more turbulent the disk becomes. And as this continues, the black hole grows at an astonishing pace. Yet even in the middle of this excess, there are limits. The light and radiation pouring outward can become so intense that it pushes back against the material trying to fall inward. This creates a strange balance, a cosmic push and pull. Sometimes the radiation is so overwhelming that it blows away part of the inflowing material, halting the feeding for a brief time before gravity pulls more in again. In this way, hyperaccretion often comes in bursts, like waves of feeding followed by short pauses. It is as if the black hole, after stuffing itself, takes a brief breath before diving back into the feast. But perhaps the most spectacular consequence of hyperaccretion is not the glowing disk itself, but the creation of jets. Jets are among the most breathtaking sights in the universe, though invisible to the naked eye. They are colossal streams of particles hurled outward from the poles of the black hole at nearly the speed of light. These jets are not made of matter that has already crossed the event horizon. Nothing can escape from there. Instead, they are formed from material just outside that ultimate boundary, caught in the grip of powerful magnetic fields. As the disk of gas and plasma swirls and spins, it generates titanic magnetic forces. Some of the inflowing material is caught, twisted, and then catapulted outward along the black hole's spin axis, like arrows fired from a cosmic bow. The scale of these jets defies imagination. They can stretch for millions of light years, piercing through galaxies, sometimes extending far beyond the host galaxy itself. A galaxy seen from across the universe may appear defined not by its billions of stars, but by the radiant jets shooting out from its core. Astronomers can detect these jets from billions of years in the past, meaning we are watching the ghosts of black holes feasting in the early universe. The power carried in these jets is beyond anything we experience on Earth. A single jet can transport more energy than entire stars produce in their lifetimes. The radiation from hyperaccreting black holes can rip electrons from atoms, ionizing entire regions of space. The jets slam into the surrounding cosmic medium, heating gas, preventing it from collapsing to form new stars. In this way, the gluttony of black holes shapes the fate of galaxies themselves, regulating how and when galaxies can grow. To put it simply, black holes in hyperaccretion are not just hungry monsters, they are cosmic architects. Their furious feeding and violent outbursts shape the evolution of the very galaxies that host them. Without such processes, galaxies might collapse differently, stars might form in different numbers, and the universe itself would not look the way it does. The imagery is astonishing. A star strays too close, shredded into ribbons of gas. The gas swirls into a fiery whirlpool millions of degrees hot. The whirlpool shines brighter than billions of stars combined, and then out of this inferno, twin beams of light and matter erupt, crossing intergalactic space. All of this is driven by the invisible maw of gravity at the centre, a black hole gorging itself in hyperaccretion. What makes this even more captivating is that such events are not rare in the deep past of the universe. In fact, some of the earliest galaxies we can observe billions of years ago were dominated by supermassive black holes undergoing hyperaccretion. These ancient monsters lit up the darkness of the early cosmos, becoming what we now call quasars, quasi-stellar objects so luminous that they could be seen across the young universe. For astronomers, quasars remain some of the brightest beacons by which we study cosmic history. Hyperaccretion is not limited to supermassive black holes alone. Stellar mass black holes, those formed from collapsing massive stars, can also undergo feeding frenzies if they are paired with a companion star. In such systems, matter streams from the unlucky companion into the black hole's grasp. If enough material accumulates, the smaller black hole too can light up like a miniature quasar, producing intense X-ray bursts detectable from Earth. The story of black hole hyperaccretion is, at its heart, a story of extremes. It is about gravity at its most intense, light at its most powerful, heat at its most searing, and motion at its fastest. It is a reminder that the universe is not a quiet, empty place, but a stage for events so violent and spectacular that they challenge our imagination. When one gazes at the night sky, the stars twinkle gently, distant and serene, yet hidden among them are these ravenous monsters, sometimes feeding modestly, sometimes erupting in cosmic banquets. In those moments of hyperaccretion, they shine brighter than entire galaxies. Their jets cut across the fabric of the cosmos, and their influence stretches across unimaginable distances. They are both destroyers and creators, devouring stars while sculpting galaxies. And all of this arises from the simplest of forces, gravity. The same force that holds us to the Earth, that keeps the moon in its orbit, that guides the planets around the sun. When concentrated into a black hole, it becomes a force of such ferocity that it can power these colossal spectacles. Black hole hyperaccretion is, without doubt, one of the grandest shows in the universe. It is a drama of hunger, violence, light, and power, played out on scales that dwarf our everyday experience. It is a reminder of the universe's wild heart, where gravity and matter dance in a frenzy that can shape the destiny of galaxies and shine across the cosmos for billions of years. When we think about the enormous size of the universe, our planet seems like nothing more than a tiny rocky speck rushing at unimaginable speed through endless space. For billions of years, the Earth has circled around the Sun, keeping to an average distance of about 150 million kilometers. But even though this sounds vast, it is only the very beginning of the story. The true size of our cosmic neighborhood, the solar system, stretches far beyond this. Modern science suggests that its farthest border, the outer edge of the mysterious and still hypothetical Oort cloud, lies at a distance of around 100,000 astronomical units. Beyond this invisible wall begins the unfathomable darkness of interstellar space, a region so empty that, on average, there is only a single lonely hydrogen atom in every cubic centimetre. The distances between stars in our part of the Milky Way galaxy measure not in kilometres, but in light years. Even though light is the fastest traveller in the universe, it still needs several years to cross the vast spaces that separate us from our nearest stellar neighbours. A photon of light leaving the Sun could make the long journey to Proxima Centauri, the closest star to us, without ever touching or colliding with even a single particle of matter. That is how thin and desolate the cosmic void truly is. This emptiness is not a rare exception, but rather a fundamental feature of the universe. It fills the Milky Way, lying between stars and planets, between black holes and white dwarfs, around scattered nebulae and dense clusters of matter. If we step outside our galaxy and look further, the picture becomes even more striking. The Milky Way itself is surrounded by an even deeper cosmic emptiness. For example, between our galaxy and the Andromeda galaxy lies a gulf of 2.5 million light-years, an unimaginably vast stretch of space so rarefied that 25 galaxies like our own could be placed within it, yet it is almost completely empty. And even this is just one small corner of the universe. The Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and roughly 100 smaller satellite galaxies are tied together by the invisible pull of gravity into a single grand structure called the Local Group. This family of galaxies stretches across about 10 million light-years, but the Local Group is not alone. It itself belongs to an even greater formation known as the Local Sheet. This flattened structure holds several hundred galaxies and spans about 46 million light-years across, with a thickness of roughly 5 million light-years. The Local Sheet in turn is a piece of the Virgo supercluster, a gigantic congregation of galaxies. Yet very near the borders of the Local Sheet, the universe suddenly changes its face. Here lies a yawning black abyss known as the Local Void. Our Local Sheet forms one of its walls, with other walls defined by the Perseus-Pisces supercluster and the Parvo-Indus supercluster. Inside, the Local Void is divided by thin galactic filaments and broad empty corridors, which connect it with neighbouring voids such as the Sculptor Void and the Hercules Void. Because of the steady expansion of the universe and the gravitational tug of matter along its boundaries, the Local Void is slowly growing larger. At present, it spans a diameter of about 150 million light-years, and the distance to its centre is at least 70 million light-years. Its nearest edge, however, lies astonishingly close, just 3.2 million light-years away from Earth. This nearness means that the Local Void takes up nearly 40% of our night sky. The bright plane of the Milky Way passes across its middle, filling that part of the void with stars and glowing nebulae, though the emptiness beyond can still be glimpsed at its edges. In the year 1854, astronomers discovered a small spiral galaxy not far north of the constellation Hercules. This galaxy was later catalogued as NGC 6553. Over time, improved observations revealed that NGC 6553 sits right inside the Local Void. Its appearance is both dazzling and unusual. Its spiral arms blaze with glowing red clouds of heated hydrogen, studded with radiant blue nebulae where new stars are born. Meanwhile, the central regions are hidden by cool brownish gas and dust. NGC 6503 measures about 30,000 light-years across and lies 17 million light-years away from us. Because of the gravitational pull of the Virgo supercluster, this galaxy is actually drifting closer to us at a speed of about 43 kilometers per second. Astronomers believe that in the distant future, perhaps after several billion years, its approach will draw in more interstellar gas, sparking a surge of new star formation. The number of young, bright stars within it may even double, causing the galaxy to shine with renewed brilliance. The slow movement of NGC 6503 illustrates how cosmic voids may have been created. The large-scale structure of the universe was born in its very earliest moments, during the chaotic mixing of energy and matter. Violent cosmic upheavals left some regions rich in matter, while others were left almost empty. Dense clumps of gas later grew into proto-galaxies, while the thin, deserted patches became voids. Over billions of years, gravity made these contrasts sharper, pulling stars and gas into galaxies and leaving the empty spaces emptier still. Observations reveal that most galaxies formed between 10 and 13 billion years ago. Remarkably, there is no difference in age between galaxies living in the heart of rich clusters and those floating in the desolate reaches of the voids. This strongly supports the modern picture of how the universe's grand architecture emerged: filaments and clusters of galaxies threading through immense gulfs of emptiness, all slowly stretching apart under the expansion of space itself. Over the course of time, astronomers believe that the region of space known as the Local Void will continue to expand and become even emptier than it already is. As this happens, the Great Virgo supercluster, which today appears as a massive cosmic gathering, will slowly begin to fall apart. It will no longer be one immense structure but will break down into several smaller independent groups of galaxies. At the present moment, the Virgo supercluster is an association of nearly 30,000 galaxies, all packed together within a sphere of space measuring about 200 million light-years in diameter. Its total weight is almost beyond imagination. Astronomers estimate it to be between 1 quadrillion and 2 quadrillion solar masses. To put that in perspective, this is roughly equal to the combined mass of about 1,000 galaxies similar to our own Milky Way. The Virgo supercluster does not exist in isolation. On one side, it is linked to other giant structures such as the Centaurus supercluster and the Pavo-Indus supercluster, forming a tangled cosmic web. On the opposite side, however, it borders a region of space so empty and dark that it seems almost unnatural. This enormous hollow is called the Taurus void, and it is one of the largest cosmic voids ever discovered. Studying the Taurus void is an astronomer's nightmare. Most of it lies in what is called the zone of avoidance, a part of the sky hidden from us by the crowded plane of the Milky Way. Here, the dazzling light of countless stars blinds us to what lies beyond, and thick clouds of interstellar dust scatter and absorb the light coming from faint distant galaxies. Fortunately, infrared observations, which can pierce through dust more effectively, have revealed at least part of the structure of this vast emptiness. The Taurus void itself is gigantic, with a diameter of about 200 million light-years and its centre located around 150 million light-years from our planet. When astronomers observe it, one of the most striking features is its astonishingly sharp boundary. On one side there is near emptiness, while right beyond lies a luminous wall of galaxies that belong to the Perseus-Pisces supercluster, one of the largest galaxy clusters in this region of the universe. Such a sudden transition is unusual. It is often seen in interstellar dust clouds, but in this case, infrared studies have found no such clouds. Many scientists think the sharp edge is shaped by the invisible hand of gravity, although the exact mechanism is still unknown. Despite its intimidating emptiness, the Taurus void may not be completely barren. The way light bends and distorts as it travels through suggests that massive unseen structures could be hidden inside. Some astronomers believe there may be huge gas and dust clouds here, potential cradles of future galaxies. Others go further and suggest that the void might contain vast stores of dark matter, the mysterious invisible substance that outweighs all visible matter in the universe and whose true nature remains unsolved. Even bolder theories propose that the centres of voids might shelter strange forms of matter, such as clumps of antimatter or even exotic matter with negative mass. These daring ideas, however, remain outside the boundaries of mainstream science, and so far there is no way to test them directly. Interestingly, despite the enormous scale of the Taurus void, only 2 galaxies have so far been found floating within its depths. The first, called UGC 2627, is a spiral galaxy that in many ways resembles our own Milky Way. The second, UGC 2629, is a much smaller elliptical dwarf galaxy. Both of these lonely islands of stars are located near the heart of the void, at a distance of about 185 million light-years from Earth. They are not very far from each other either, separated by only a few hundred light-years. It is possible that other galaxies also drift silently within the void, but the Milky Way's bright disk continues to block our view. The Virgo supercluster itself is not alone in its grandeur. Together with 4 other neighbouring superclusters, it forms a gigantic cosmic structure known as Laniakea, a colossal galactic filament. Laniakea contains over 100,000 galaxies and stretches for more than 500 million light-years across space. At its heart lies the Great Attractor, a mysterious concentration of mass located about 250 million light-years from us, whose gravity tugs relentlessly on the galaxies around it. But even this is not the end of the story. Laniakea itself is part of a far larger network, one that is surrounded by an abyss unlike anything else ever seen. Beyond it lies a cosmic void of unprecedented proportions, an expanse so immense and so empty that even the faint glow of distant galaxies is drowned in its darkness. According to calculations, even elusive neutrinos, particles that can travel unhindered through nearly everything, would take billions of years to cross this yawning gulf. What is perhaps most astonishing is how recently this enormous void was discovered. Despite all our powerful telescopes and sophisticated methods of observation, astronomers only noticed it about 10 years ago, in the year 2013. It was during this year that a team from the University of Wisconsin-Madison, led by Professor Amy Barger, made the startling find while measuring distances between galaxies. To their amazement, they realized that Laniakea and the superclusters around it are wrapped in a gigantic cosmic void, larger than anything ever seen before. The void turned out to be so large that it challenged some of the most basic assumptions of cosmology. Its existence suggests that the universe is not only more mysterious, but also far more complex and elaborate than anyone had dared to imagine. In recent years, one of the most astonishing discoveries in astronomy has been credited to 3 researchers: Amy J. Barger, Ryan Keenan, and Lennox Coy. Their work revealed something extraordinary. Our own galaxy, the Milky Way, together with its nearby companions, is located inside the very heart of the largest known cosmic void. This immense region of space, mostly empty of galaxies, was named the KBC void, after the initials of the scientists who uncovered it. According to astronomical observations, this enormous cosmic hollow is nearly spherical in shape, with an estimated diameter of more than 2 billion light-years. To put that into perspective, this makes it one of the most gigantic structures known in the universe. The Milky Way itself lies not exactly at the centre of this void, but rather a few hundred million light-years from its conditional midpoint, and roughly the same distance from its edge. The discovery of this great cosmic bubble helped explain a puzzling mystery that had troubled scientists for decades. It is well known that all galaxies in the universe are drifting apart as space itself expands, a process described by the Hubble constant, a number that tells us how quickly the universe grows. But when astronomers tried to calculate this constant using galaxies close to us, they found that the universe appeared to be expanding too slowly. On the other hand, when using very distant galaxies, the opposite result was obtained. The universe seemed to be expanding too fast. This contradiction was a major cosmic riddle. The KBC void provided an elegant answer. Because our galaxy and its neighbours lie inside this enormous empty bubble, they are constantly being pulled by the gravitational influence of the faraway matter that surrounds the void. This stretching effect subtly alters the apparent speed of expansion, depending on whether nearby or distant galaxies are used as the measuring stick. Even more surprising is that the KBC void is not just a hollow patch of space, but a vast structure that contains within it smaller voids and even whole superclusters of galaxies. For example, the local void and the Taurus void are both part of its enormous framework. Compared to other cosmic voids, the KBC may seem unusually large, but interestingly, it is not completely empty. It still contains galaxies, filaments, and clusters, just fewer than average. Still, when compared to the universe as a whole, the KBC void is almost invisible. The observable universe itself spans about 92 billion light-years across, making even this colossal bubble appear as just a faint dark smudge on the cosmic map. When astronomers map the universe in detail, they find many other voids scattered across the cosmic web. Most of these dark patches fit neatly into existing physical theories, but some display truly baffling features. Among them, one of the most mysterious is the Eridanus supervoid, better known as the CMB cold spot. This structure is estimated to be between 500 million and 1 billion light-years wide, and it lies at a distance of roughly 6 to 10 billion light-years from Earth. It is located in the southern part of the sky and covers a patch several times larger than the full moon, yet it is not visible to the naked eye. It can only be detected using sensitive telescopes that study the universe in the microwave part of the spectrum. What makes the cold spot so fascinating is the unusual behaviour of the ancient radiation from the Big Bang, known as the Cosmic Microwave Background, CMB. Inside this region, the radiation is about 70 microkelvin cooler than the average temperature of the universe. That may seem tiny, but it is nearly 4 times stronger than any anomaly recorded before, and given its huge size, it has become one of the greatest cosmic enigmas of our time. Scientists currently believe that the radiation passing through this supervoid loses some of its energy due to the pull of faraway clusters of galaxies, which makes it appear colder. However, calculations show that this gravitational effect can explain only about 1/4 of the cooling. The remaining 3/4 may hint at something even more mysterious: the presence of hidden dark matter or dark energy influencing the radiation in ways we do not yet understand. For now, the cold spot, like the KBC void itself, stands as one of the universe's most intriguing riddles. Quasars are among the most astonishing wonders of the universe, blazing like cosmic beacons that can outshine entire galaxies. Their very name carries a story. The term quasar is a shortened form of quasi-stellar radio source. This label was first given to them in the middle of the 20th century because, When astronomers detected them for the very first time, they seemed to resemble stars. Through radio telescopes, these mysterious objects appeared as tiny points of light, looking deceptively like distant suns, yet they emitted powerful streams of radio waves unlike anything normal stars could produce. At first, scientists thought they were simply peculiar stars, but careful study revealed something far more dramatic. These were not stars at all, but incredibly energetic objects located at the very centres of distant galaxies, powered by titanic engines known as supermassive black holes. The discovery of quasars in the early 1960s was nothing less than revolutionary. Until then, astronomy had already uncovered galaxies, nebulae, pulsars, and even radio galaxies. But quasars introduced a completely new class of celestial phenomena, objects so bright and energetic that they shattered previous assumptions about how much power the universe could generate. To put it into perspective, a single quasar can release more energy than the combined light of all the hundreds of billions of stars contained in its host galaxy. Imagine one small point of light blazing so fiercely that it completely outshines the vast sea of stars around it. That is the spectacle of a quasar. What fuels this astonishing brilliance? The answer lies in the heart of their host galaxies. At the centre of a quasar lurks a supermassive black hole, often weighing millions or even billions of times more than our Sun. Normally, black holes are thought of as invisible monsters, swallowing all light and matter that come too close. But under the right circumstances, when vast amounts of gas, dust, and even entire stars fall towards such a black hole, the infalling material forms what scientists call an accretion disk. This swirling disk of matter heats up to unimaginable temperatures as it spirals inward, glowing with dazzling radiation. The process converts gravitational energy into light and heat with astonishing efficiency. In fact, the energy released by material falling into a black hole can be far greater than the energy produced by nuclear fusion inside stars. This is why quasars shine so brightly. They are supermassive black holes caught in the act of ravenous feeding, blazing like cosmic furnaces visible across the universe. When astronomers first identified quasars in the 1960s, it challenged everything they thought they knew about the cosmos. Their sheer brightness seemed impossible. How could such distant objects, located billions of light years away, still appear so luminous to our telescopes on Earth? The only answer was that they must be producing unimaginable amounts of energy. At that time, many astronomers struggled to accept that black holes could truly exist. Quasars, however, provided overwhelming evidence that not only do black holes exist, but when they are actively consuming matter, they become some of the brightest and most powerful objects in the entire universe. But quasars are not frozen in time. Like living creatures, they have life cycles. A quasar becomes active when its central black hole is voraciously feeding, pulling in material from its surroundings at a rapid pace. This phase can last millions of years. During this time, the galaxy's core blazes with such intensity that it may outshine everything else in the galaxy combined. Yet the feast cannot last forever. Eventually, the black hole consumes most of the nearby material, or powerful winds and radiation blow the remaining gas and dust away. When the supply of fuel runs low, the once blazing quasar fades. The active galactic nucleus becomes quiet and dormant. The black hole still remains at the centre, massive and powerful, but without the bright fireworks that once defined it. The galaxy may then appear as a normal elliptical or spiral galaxy, with a silent central black hole that is no longer feeding vigorously. It is important to note that not every supermassive black hole becomes a quasar. Many galaxies, including our own Milky Way, contain such enormous black holes at their centres. However, most of them are relatively quiet, either because they lack enough surrounding material to consume, or because their feeding process is too slow to generate the blinding light of a quasar. A galaxy becomes a quasar only during those rare, dramatic times, when huge amounts of gas and dust pour into the black hole at once, triggering the furious energy release that makes the galaxy's centre glow brighter than everything else around it. The influence of quasars is not limited to their host galaxies. Their power extends outward into the surrounding universe. The radiation they produce can ionize nearby gas clouds, stripping electrons from hydrogen atoms and creating vast regions of hot, charged plasma. This process, known as reionization, was especially significant in the early history of the universe. In the first few 100 million years after the Big Bang, the universe was filled with a foggy sea of neutral hydrogen gas. Light could not easily travel through this haze, making the cosmos opaque. Then came the age of rionization, driven partly by young stars and partly by the furious energy of quasars. Their blazing radiation transformed the fog into transparent space, allowing light to travel freely and making the universe clear. Without quasars and their immense energy, the universe might still be cloaked in a murky veil, and we would not be able to see the distant galaxies that populate the cosmos today. One of the most remarkable aspects of quasars is the vast distance from which we can observe them. The light from the most distant quasars has travelled for more than 13 billion years before reaching Earth. This means that when we peer through our telescopes and capture the glow of a faraway quasar, we are actually looking deep into the past, seeing the object as it appeared when the universe was still in its infancy. Quasars, therefore, are like cosmic time machines. They give astronomers rare glimpses into the conditions that existed billions of years ago, showing how galaxies were born, how black holes grew, and how the universe itself evolved. Let us pause for a moment to consider the scale of this. The universe is estimated to be around 13.75 billion years old. Some of the quasars we can see today were already shining brightly when the universe was less than 1 billion years old. That means these quasars were among the very first massive objects to form after the Big Bang. They tell us that black holes, far from being rare or slow to form, appeared very early in cosmic history and quickly grew to staggering sizes. How exactly they managed to grow so fast is still one of the great mysteries of astrophysics. Did they begin as the remnants of the very first generation of stars, or did they form through the direct collapse of enormous gas clouds in the young universe? Quasars hold the clues to these cosmic riddles. Another fascinating fact about quasars is their variability. Unlike ordinary stars, which usually shine steadily for billions of years, quasars can flicker and change in brightness over much shorter timescales, sometimes even days or weeks. This variability tells scientists that the regions producing the light are relatively compact, no larger than our solar system. Such small regions producing such vast energy output again points to the presence of supermassive black holes as the engines of quasars. The study of quasars has also provided astronomers with useful tools for measuring the universe. Because quasars are so bright, they can be seen across immense distances. This makes them valuable as lighthouses that illuminate the otherwise dark stretches of space. By analysing the light from quasars, scientists can detect the presence of intergalactic gas lying between us and the quasar. As the light travels through space, it passes through clouds of hydrogen and other elements, which leave subtle fingerprints in the spectrum of the quasar's light. These fingerprints reveal the composition, temperature, and movement of the gas, giving scientists a way to map the invisible structures of the cosmos. In this way, quasars not only serve as objects of study in themselves, but also as tools that help us learn about the universe as a whole. The impact of quasars on their host galaxies can be profound. The radiation and winds they release can blow away gas from the galaxy, shutting down star formation. In this sense, quasars may play a role in shaping the evolution of galaxies, deciding how many stars they can form and how they develop over billions of years. Some astronomers even suggest that without the regulating influence of quasars, galaxies might grow too large or form too many stars too quickly. In this way, the violent outbursts of quasars may help maintain balance in the cosmic ecosystem. To fully appreciate quasars, one must imagine the scene at the core of an active galaxy. Picture a swirling maelstrom of gas and dust, spiraling inward at incredible speeds. The disk glows with brilliant light, hotter than the surface of most stars. Jets of material may shoot outward from the poles of the black hole, blasting radiation across millions of light years. The entire galaxy becomes dominated by the central engine, its stars reduced to a faint background compared to the brilliance of the core. For astronomers, observing such a spectacle is like watching the universe at its most extreme, a place where gravity, energy, and matter interact in the most violent ways possible. And yet, as dazzling as they are, quasars are also fleeting on cosmic timescales. A quasar may remain active for tens of millions of years, but compared to the lifespan of galaxies, which can last for tens of billions of years, this is just a brief flare of light. Once the feeding frenzy ends, the galaxy settles down, leaving behind only the silent black hole as a reminder of the quasar's former glory. Our own Milky Way may have once been a quasar in its youth, and it is possible that in the far future, under the right conditions, it could flare up again. Thus, quasars are not only extraordinary phenomena in themselves, but also keys to understanding the grand story of the universe. They reveal the presence and growth of black holes, the transformation of galaxies, and the evolution of cosmic structures. They help explain how the early universe changed from opaque to transparent, allowing us to see the stars and galaxies that now fill the night sky. They serve as tools for probing the vast distances of space, illuminating regions that would otherwise remain hidden. And above all, they remind us of the staggering power that lies hidden within the universe, waiting to be unleashed when matter and gravity collide in the heart of a galaxy. Quasars, then, are not just luminous objects. They are the blazing signatures of creation and transformation on the largest scales. They tell a tale of hunger and light, of black holes consuming the universe's raw materials, and in doing so creating the most spectacular light shows the cosmos has ever known. When we gaze upon a quasar's ancient light, we are not merely looking across space, we are looking back in time, glimpsing the dawn of galaxies and the first chapters of cosmic history. Blazars are one of the most fascinating and extraordinary cosmic objects that humanity has ever discovered. To truly appreciate them, it is important to understand that the universe is not a quiet or static place. It is alive with violent forces, with immense explosions, with light that has travelled across billions of years, and with colossal black holes that consume everything unlucky enough to drift too close. In the very heart of certain galaxies, something remarkable occurs when a gigantic black hole feeds with great intensity, swallowing enormous amounts of matter while also unleashing powerful jets of energy. When these jets, by chance, are directed almost exactly along our line of sight here on Earth, the galaxy transforms into what astronomers call a blazar. A blazar is a special and rare class of what scientists name active galactic nuclei, often shortened to AGN. An active galactic nucleus is the central region of a galaxy, where a supermassive black hole is not resting quietly, but instead is feasting on material such as stars, gas clouds, and interstellar dust. The act of consuming matter generates titanic amounts of energy, far greater than what is produced by the combined light of all the billions of stars that fill that galaxy. But among all the different types of active galactic nuclei, blazars stand out because of their orientation. Their unique position relative to Earth allows us to witness their might in a way no other object can rival. At the core of the process lies the black hole's accretion disk. Imagine a swirling whirlpool of blazing hot gas, spinning furiously around the black hole, gradually spiralling inward toward its dark centre. As this gas and dust fall deeper, they heat up and emit tremendous energy, producing radiation that can stretch across the entire electromagnetic spectrum. Yet not all of the energy is swallowed. Instead, the black hole and its surrounding magnetic fields channel part of this energy into two colossal jets that blast outward in opposite directions, aligned with the black hole's axis of rotation. These jets can stretch for thousands of light years, cutting across interstellar space like twin cosmic lighthouses. Most galaxies with active black holes have jets that point in random directions. If the jet does not point anywhere near Earth, we see the galaxy's nucleus in a more muted way, even though it may still be very powerful. But in the case of a blazar, fortune places us directly in the path of one of these jets. To put it more vividly, it is as though the universe has aimed a cosmic spotlight directly at us. Because the jet is aligned with our line of sight, its radiation is magnified by what physicists call relativistic boosting, a phenomenon explained by Einstein's theory of special relativity. Relativistic boosting can be understood in simple terms. When particles travel very close to the speed of light, the energy they radiate becomes concentrated and directed forward along the direction of motion. This means that if we are looking almost straight into the path of that beam, the light and radiation appear far brighter, more energetic and more intense than they would otherwise. It is a trick of cosmic physics that turns an already powerful source into something that outshines entire galaxies. Light waves are compressed in the direction of motion, so they reach our telescopes packed with extra energy. As a result, the blazar looks like one of the most luminous objects in the entire universe, even though the galaxy itself may be unimaginably far away. What makes this effect even more astonishing is that the energy from a blazar's jet can surpass the energy coming directly from the accretion disk itself. Instead of the energy being spread in all directions, the jet focuses it like a high-powered laser beam aimed toward Earth. The outcome is that blazars shine across the cosmos as some of the brightest beacons known to science. In some cases, a single blazar can rival, or even outshine, the collective glow of hundreds of billions of stars in a galaxy. That is how extreme their power can be. Another curious and captivating trait of blazars is their variability. Unlike many other cosmic sources of radiation that remain steady over time, blazars flicker and fluctuate, sometimes on astonishingly short timescales. Their brightness can surge or diminish within a matter of a few days, and sometimes even within a few hours. Imagine watching a faraway lighthouse in the deep ocean of the cosmos, only this lighthouse does not rotate with a calm, predictable rhythm, but instead pulses, flares, and dims with wild intensity. This restless variability is caused by the turbulent, violent conditions within the jet itself. Particles inside it are constantly being accelerated to near-light speeds, colliding with magnetic fields, crashing into each other, and releasing bursts of energy that change rapidly with time. For astronomers, this flickering light is not just a beautiful phenomenon, but also a scientific treasure. It acts like a coded message sent from the very edge of a black hole, giving insights into processes that cannot be observed directly. Because the jet is pointed straight at us, we gain a rare opportunity to peer into the innermost regions of a galaxy's heart. Each fluctuation in brightness, each pulse of energy, is a clue about the mechanisms at work near the black hole. Mechanisms involving shock waves, magnetic disturbances, and violent flows of matter that shape the cosmic landscape around the abyss. The energy from a blazar is not confined to visible light alone. In fact, blazars are remarkable because they pour out radiation across the entire electromagnetic spectrum. This means they emit everything from low-energy radio waves, which can span across galaxies, to the most energetic gamma rays, which carry incredible power. At the lower end, the radio emissions come from what scientists call synchrotron radiation, which is produced when charged particles spiral around magnetic fields at near-light speeds. But as these particles are pushed to even higher energies, they begin to produce X-rays and gamma rays, some of the most extreme forms of light known in physics. In certain circumstances, the energy from a blazar can even produce gamma ray bursts. These are short but immensely powerful flashes of radiation that can be detected from billions of light years away. They are among the most energetic events in the cosmos, and when they occur in connection with a blazar, they reveal the sheer ferocity of the processes inside those relativistic jets. Because blazars are so luminous, they can be seen across incredible distances. Some of them are located billions of light years away, yet they remain visible to our telescopes as though they were much closer. In this way, blazars serve as natural cosmic lighthouses, guiding astronomers as they study the farthest corners of the universe. Observing blazars allows scientists to look back in time, since the light we see today may have left the galaxy billions of years ago, long before our planet even existed. In this sense, every blazar acts like a time machine, offering glimpses of the young universe, the growth of supermassive black holes, and the ways galaxies evolve through cosmic history. But the usefulness of blazars does not end with studying black holes alone. As their light travels across intergalactic space, it interacts with everything in its path. Clouds of gas, scattered particles, and the vast but faint medium that fills the emptiness between galaxies can all affect the radiation before it finally arrives on Earth. By carefully analysing these changes, astronomers can learn about the density, composition, and structure of the intergalactic medium. In this way, blazars provide valuable information about the large-scale structure of the universe itself, acting as probes of the cosmic web that stretches across space. One of the most famous blazars ever discovered is the quasar known as 3C279. This extraordinary object is located more than 5 billion light-years away, and yet it shines with such brilliance that it has become one of the most closely studied blazars in the sky. Its intense and variable radiation has been observed countless times by astronomers using both ground-based telescopes and space-based observatories. Through 3C279, scientists have been able to test and refine their theories about how relativistic jets operate, how black holes manage to accelerate matter to such extraordinary speeds, and how these processes connect to the behavior of galaxies as a whole. In recent years, new observatories have expanded our view of blazars even further. Instruments like the Fermi Gamma Ray Space Telescope have detected blazars in high-energy gamma rays, giving researchers new tools to study their extreme emissions. These observations help reveal not only the mechanics of jets, but also the hidden properties of the universe itself. Blazars even provide clues about two of the greatest mysteries in modern science: dark matter and dark energy. These two invisible components together make up most of the mass energy of the universe, yet their nature remains largely unknown. By studying how the light from blazars is bent, absorbed, or altered as it travels through space, scientists can infer the influence of dark matter and dark energy on cosmic structures. In this way, blazars become more than just powerful beacons. They turn into instruments of cosmology, tools that may one day help us answer the most profound questions about existence. Blazars, then, are not merely distant curiosities. They are windows into the deepest mysteries of the cosmos. They are both destructive and illuminating, violent yet beautiful, terrifying yet inspiring. Their brilliance is a reminder of how much power the universe holds, and their study reveals to us how galaxies grow, how black holes shape their environments, and how the invisible fabric of space itself behaves. To gaze upon a blazar is to witness the raw forces of creation and destruction at work, magnified by the strange tricks of relativity and delivered to us across unfathomable stretches of space and time. Imagine a star, a brilliant glowing sphere of gas, shining for millions or even billions of years. It drifts peacefully in its galaxy, surrounded by countless other stars, planets, and clouds of dust. To most of these stars, their long lives pass without ever encountering anything that would endanger them, except for the gradual burning of their fuel, which will one day cause them to grow old and fade. But for some unlucky stars, their end is far more sudden, violent, and spectacular. These are the stars that stray too close to a monster hidden in the hearts of galaxies, the supermassive black hole. When a star approaches one of these titans of gravity, the difference in pull between the side of the star nearest to the black hole and the side farthest away grows stronger and stronger. This stretching force is what scientists call tidal gravity. The same kind of force exists on Earth. The moon pulls on the oceans more strongly on the side facing it, causing the water to bulge out into what we call tides. But while the moon's tidal pull only shifts our oceans by a few feet, a black hole's tidal force is unimaginably stronger. If a star drifts too close, it does not simply feel a little tug. It begins to stretch like a piece of soft dough being pulled apart. The closer the star moves to the black hole, the greater this imbalance becomes, until the star can no longer hold itself together. At that moment, the star is torn to pieces. This incredible event is known as a tidal disruption event, often shortened to TDE. It is one of the most dramatic and catastrophic processes in the universe, a cosmic act of destruction that lights up space for weeks or months before fading away. The way the star is pulled apart is almost poetic in its brutality. At first, the star elongates slowly, like a rubber band being stretched. Then, as it crosses the point of no return called the tidal radius, the stretching accelerates until the star rips apart completely. Its gases, once bound tightly by gravity and pressure in a glowing sphere, are flung outward in a chaotic stream. Some of the star's matter escapes into space, hurled far beyond the black hole's grasp, while the rest spirals inward toward the monster that destroyed it. The sight, if we could ever witness it up close, would be beyond breathtaking. As the gas and plasma from the star swirls around the black hole, it heats to extraordinary temperatures. Friction between streams of material colliding at incredible speeds generates heat so extreme that it gives off dazzling radiation. This radiation is not the gentle light we see from ordinary stars, but an intense outpouring of high-energy forms, especially ultraviolet rays and X-rays. These wavelengths are invisible to our eyes but detectable by telescopes, and they shine so brightly that, for a brief period, the flare of a tidal disruption event can outshine the combined light of every star in the black hole's entire galaxy. Think about that for a moment. A galaxy can hold hundreds of billions of stars, each one shining like a small sun. Yet the destruction of a single star near a black hole can produce more light than all of them together, sometimes shining several hundred times brighter. For weeks or months, this flare becomes a beacon visible across enormous cosmic distances, a lighthouse signaling the violent power of black holes. But how does a star end up wandering so close to danger in the first place? Most stars orbit quietly around the centers of their galaxies without incident. Yet galaxies are busy places, and stars do not move through them in isolation. They are constantly influenced by the pull of their neighbours, by clusters of stars, by clouds of gas, and by the invisible hand of dark matter shaping the galaxy's gravity. Sometimes, these interactions nudge a star onto a new path, pushing it closer to the centre where the black hole lurks. In other cases, a star may be part of a system with multiple stars, and the complex dance of gravity between them sends one spiralling inward toward destruction. There are even rogue stars, lonely travellers wandering without a fixed orbit that may accidentally pass near the black hole's sphere of influence. Whatever the reason, once a star drifts too close, inside that critical tidal radius, its fate is sealed. As the star breaks apart, its debris spreads outward in all directions. Imagine a glowing cloud of gas, expanding rapidly and radiating heat. Some of this material moving too fast escapes into interstellar space, but much of it is captured by the black hole's gravity and falls inward, circling like water spiralling down a drain. This swirling matter forms a temporary accretion disk, a glowing ring of hot gas that emits brilliant light as it spirals toward the event horizon. For a short while, this disk becomes one of the brightest objects in the universe. The violence of the process does not stop there. The energy released during the tearing of the star can launch shockwaves that ripple through the surrounding gas and dust. These shockwaves compress and heat the interstellar medium, disturbing its calm balance. The black hole itself may even launch jets of material at nearly the speed of light, blasting the surrounding galaxy with streams of high-energy particles. The remains of the star are not wasted. They enrich the galaxy with heavier elements that had been forged inside the star during its lifetime. When the debris mixes with interstellar gas, it seeds the galaxy with the ingredients needed for future generations of stars and planets. In this way, the violent death of one star may contribute to the birth of countless others. For astronomers, tidal disruption events are more than just spectacular displays. They are windows into the hidden world of black holes. Black holes themselves cannot be seen directly, since their gravity traps even light, but when they destroy a star, they announce their presence in the brightest possible way. By studying the flare of radiation, scientists can learn about the black hole's properties, its mass, its spin, and the way it consumes matter. The pattern of light over time, the way it brightens, fades, and shifts in colour, reveals details about the physics of the accretion process. It tells us how matter behaves under conditions that no laboratory on Earth could ever reproduce. Despite all we have learned, tidal disruption events remain full of mysteries. Astronomers still debate exactly how the shredded material of a star rearranges itself. Does it form a neat, thin disk that orbits steadily around the black hole? Or is it thrown into space in turbulent streams, creating a chaotic storm of gas? What role do magnetic fields play in shaping the outflows? How do the shock waves affect the galaxy around them? These are questions scientists are still working to answer, using telescopes that capture X-rays, ultraviolet light, and even the faint whispers of gravitational waves. What makes these events especially challenging to study is their fleeting nature. Unlike quasars, which shine for millions of years, or supernovae, which unfold over months and then leave a long-lasting remnant, tidal disruption events burn brightly but briefly. A few weeks or months is all they last. By the time astronomers notice one, it may already be fading. Catching the earlier stages requires constant vigilance, scanning the skies with wide-field telescopes that can detect sudden bursts of light. Even then, every event is unique, with its own peculiarities depending on the size of the black hole, the mass of the star, and the exact angle of their encounter. To put the scale of a tidal disruption event into perspective, imagine this. If a star like our Sun were torn apart by a black hole, the energy released could briefly rival the brightness of the Milky Way galaxy itself. The Sun contains enough mass and fuel to shine for billions of years, but in the hands of a black hole, much of that energy could be unleashed in a matter of weeks. It is the ultimate cosmic paradox, where destruction creates illumination. Yet even in their violence, tidal disruption events play a role in the grand balance of the universe. Black holes grow by consuming the matter of stars that wander too close, and their growth shapes the evolution of galaxies. The flares they produce can regulate star formation in their surroundings, heating and disturbing gas that might otherwise collapse to form new stars. Thus, the tearing apart of one star can influence the destiny of an entire galaxy. astronomers are only beginning to grasp the full importance of these events. In recent years, with new telescopes and advanced sky surveys, more tidal disruption events have been discovered than ever before. Each one adds a piece to the puzzle, helping scientists refine their theories. In the future, as observatories become more powerful and as instruments capable of detecting gravitational waves and neutrinos advance, we may be able to watch these events unfold in even greater detail. Perhaps we will finally answer the questions about how exactly a star's last moments play out as it is shredded by gravity. Still, there is something deeply humbling about these cosmic catastrophes. They remind us that the universe is a place of extremes, where beauty and violence often walk hand in hand. A star that has burned peacefully for billions of years can meet its end in a matter of days when it strays too close to the wrong place. Its light, spread across countless parsecs, may shine into the eyes of astronomers on a tiny planet orbiting an ordinary star, allowing us to witness an ending that is both tragic and awe-inspiring. Tidal disruption events are more than scientific curiosities. They are stories written in light, tales of stars that lived long lives only to be ripped apart by the dark hearts of galaxies. For a brief time, their deaths illuminate the cosmos, letting us glimpse the power of black holes and the fragile beauty of stars. They are fleeting, unrepeatable, and unforgettable. Gamma-ray bursts, often called GRBs for short, are among the most extraordinary and powerful events known to humankind in the vast universe. These events are so bright and so energetic that for a brief moment they can outshine entire galaxies filled with billions upon billions of stars. Scientists, after many years of study, have realized that not all gamma-ray bursts are the same. To bring order to these strange cosmic fireworks, astronomers have created a kind of classification system, a taxonomy of sorts, where bursts are placed into categories depending on how long they last. At first, this might sound like a very simple way to divide them, but in truth, the length of time a burst shines is not just a matter of counting seconds or minutes. The duration of a gamma-ray burst holds deep secrets about the forces that created it, about the kind of stars or celestial objects that gave birth to this radiant catastrophe, and about the hidden processes unfolding in the universe at unimaginable distances from us. The broad classification recognized today divides these bursts into three main kinds. There are short bursts, there are long bursts, and then there is a mysterious middle ground that does not fully fit into either group. Each category has its own story to tell, and together they form a cosmic puzzle that is still far from being completely solved. What makes this all the more fascinating is that behind these bursts, which often last no longer than the blink of an eye, lie events of almost unimaginable violence and importance. Entire stars die in order to create them. Neutron stars crash together with a force that bends space-time itself. Supernova explosions release their final breath in a blaze of light. And sometimes, something even stranger takes place, something that keeps astronomers awake at night, wondering whether they are looking at a completely new type of celestial disaster. The short gamma-ray bursts are the first group in this cosmic taxonomy. The name short might sound modest, but these are anything but mild. A short gamma-ray burst is typically over in less than 2 seconds, and many do not even last a full second. Some vanish in a fraction of a moment, shorter than the time it takes to blink your eyes. Yet within that sliver of time, the energy that is released is staggering. Imagine the sun, our familiar star, shining as it does steadily for about 10 billion years. Now imagine that same amount of energy, or even more, being unleashed in less than a second. That is the power of a short gamma-ray burst. To humans on Earth, such an event happening nearby would be catastrophic, but thankfully most of these bursts occur in galaxies that are billions of light years away, so they are reduced to fleeting flashes of radiation that only our most sensitive instruments can detect. Where do these short bursts come from? Over the years, scientists have gathered evidence that points toward one of the most violent and dramatic events possible in the universe, the merger of two neutron stars. A neutron star is the compact remnant left behind after a massive star has exploded as a supernova. Although only about 20 kilometers wide, a neutron star holds more mass than our Sun. Its density is so extreme that a single teaspoon of neutron star material would weigh billions of tons. When two of these objects form in the same system and slowly spiral toward one another over millions or even billions of years, their final dance ends in a catastrophic collision. When they finally merge, The energy released is so tremendous that it blasts out gamma radiation across the universe. These cosmic collisions not only produce short gamma-ray bursts, but are also believed to forge some of the heaviest elements in nature, such as gold and platinum. In this way, every short burst may be connected to the very materials that eventually form planets, jewellery, and even parts of our bodies. Long gamma-ray bursts tell a different story. Unlike the fleeting short bursts, these can last for tens of seconds or even several minutes. Some continue blazing for as long as 5 or 6 minutes, which in the realm of gamma radiation is an eternity. Their origin lies in a completely different kind of event, the death of a massive star. When a star that is at least 30 times heavier than our Sun nears the end of its life, it can no longer sustain the nuclear reactions in its core that have been keeping it stable for millions of years. Without that support, gravity takes over and the star's core collapses. The collapse is so sudden and so intense that it often results in the formation of a black hole, a region where gravity is so strong that nothing, not even light, can escape. But before the black hole fully swallows everything, the star releases a staggering outpouring of energy. The outer layers of the star may explode outward as a supernova, while at the same time jets of material are blasted away at nearly the speed of light. These jets, if they happen to be pointed in the direction of Earth, are seen by our instruments as long gamma-ray bursts. Thus, behind each long burst is the tragic but magnificent death of a giant star. In some sense, every long burst is the funeral fire of a stellar titan, a cosmic farewell that echoes across the universe. Then comes the enigmatic third group, the ones that fall somewhere between short and long. These intermediate bursts usually last for a few seconds, sometimes stretching toward a minute, but not quite as long as the classic long bursts. They puzzle astronomers because they do not clearly fit either category. Their behaviour hints that they might be caused by something entirely different from both neutron star mergers and the deaths of extremely massive stars. One possibility is that they come from stars that are massive enough to collapse, but not as massive as those that produce the longest bursts. Another idea is that they may result from unusual mergers, such as a neutron star colliding with a black hole. But the truth remains uncertain. Each time astronomers capture one of these intermediate bursts, they are reminded that the universe still holds secrets that resist simple classification, that there may be cosmic events waiting to be discovered that we do not yet fully imagine. The environments in which these different bursts are found also provide important clues. Long gamma-ray bursts are usually detected in young, active galaxies, the kinds of galaxies where new stars are constantly being born. This makes sense, because massive stars do not live long lives. They burn hot and fast, exhausting their fuel within just a few million years, so their deaths, and thus their bursts, must occur in regions where stars are still forming. In contrast, short bursts are often found in older galaxies. In these quieter galaxies, the formation of new stars has slowed down, but the old neutron stars that were born long ago still exist. Over long stretches of time, these compact stars may drift closer to one another until they merge, unleashing their brief yet furious outburst of gamma rays. In this way, the location of a burst helps astronomers trace its ancestry, telling whether it came from the fiery life of a young massive star or from the patient, drawn-out dance of two ancient compact stars. As if this picture were not already complex enough, astronomers have discovered an even stranger and rarer kind of gamma-ray burst, the so-called ultra-long gamma-ray bursts. These events stretch the boundaries of what was once thought possible. Instead of lasting seconds or minutes, these extraordinary bursts can endure for thousands of seconds, sometimes more than an hour. Imagine a cosmic beacon blazing in gamma rays for such a long stretch of time. It is unlike almost anything else in the heavens. The discovery of these bursts has challenged many of the old ideas about stellar evolution and the mechanisms behind gamma-ray bursts. If short bursts come from neutron star mergers, and long bursts come from the collapse of giant stars, then what could possibly create a burst that continues for over an hour? The first well-studied case of an ultra-long burst was seen in the year 2011. This burst, given the technical name GRB 1129A, stayed bright for over an hour before it finally faded away. Since then, astronomers have recorded several other events of this kind, but they remain puzzling and rare. They do not easily fit into the usual models. One leading idea is that ultra-long bursts may come from the collapse of especially massive stars known as blue supergiants. These stars are huge and extremely hot, burning through their nuclear fuel at a ferocious rate. When they finally run out of fuel, their collapse might not be as fast and clean as with smaller massive stars. Instead, the collapse may drag out, producing a more gradual release of energy that can sustain a gamma-ray burst for much longer. Another possibility is that ultra-long bursts might come from something altogether different, such as tidal disruption events. In a tidal disruption event, a star wanders too close to a supermassive black hole and is torn apart by the overwhelming pull of gravity. The remains of the star form a swirling disk of matter around the black hole, heating up to astonishing temperatures. If enough of that energy is channeled outward in the form of radiation, it might produce a prolonged gamma-ray burst that lasts far longer than usual. In this view, the ultra-long burst is not just a stretched version of a normal burst, but something fundamentally distinct, a slow and sustained cosmic inferno. What makes ultra-long bursts so intriguing is that their energy often does not arrive in a single violent pulse. Instead, it comes as a series of flares or as a long, gradually fading glow. This difference in structure suggests that the processes fueling these events are more extended, perhaps involving the slow collapse of stellar material or the steady feeding of a black hole. Ultra-long bursts are often detected in distant galaxies billions of light-years away, but unlike long bursts, they are not confined to any particular type of galaxy. Some appear in star-forming galaxies, while others have been found in more unusual environments. This variety implies that their origins depend less on the galaxy they are in, and more on the special properties of the star or black hole involved. Detecting these ultra-long bursts is not easy. Traditional gamma-ray observatories are designed to catch bursts that flash quickly, often within just a few seconds. To spot a burst that lingers for thousands of seconds requires continuous monitoring and careful analysis. Sometimes, by the time astronomers realize that an event is unusual, it has already faded. To capture them properly, researchers use both satellites in orbit, which can detect the high-energy radiation, and telescopes on the ground, which can watch for the afterglow in visible light and other wavelengths. As newer, more sensitive instruments are built, the number of detected ultra-long bursts is likely to grow, and with them, our understanding of these strange events will deepen. Perhaps in the years to come, astronomers will find that there are even more categories of gamma-ray bursts than the ones we now know. In the grand scheme of things, gamma-ray bursts remind us of the universe's wild unpredictability. They show us that the life of a star can end in many different ways, sometimes quickly, sometimes violently, sometimes gradually, and sometimes in ways we're only just beginning to imagine. They reveal that black holes, those mysterious objects that hide behind horizons of no return, can also be engines of light that momentarily illuminate the darkness of space. They hint that galaxies, whether young and vibrant or old and quiet, are still theatres of drama and transformation. And they remind us that even though we have built satellites and telescopes capable of peering billions of light-years into space, we are still only at the beginning of understanding the full richness of cosmic events. The taxonomy of gamma-ray bursts, short, long, intermediate, and ultra-long, is more than just a set of labels. It is a map of possibilities, each pointing toward a different kind of cosmic ending. The short bursts whisper of ancient neutron stars locked in fatal embraces. The long bursts cry out the deaths of giant stars collapsing into black holes. The intermediate bursts tease us with riddles not yet solved, and the ultra-long bursts roar with mysteries so deep they may yet overturn much of what we think we know about the universe. Each time one of these bursts is detected, for a brief moment the universe is speaking in its own fiery language, telling stories of creation and destruction, of endings that give birth to new beginnings. And while we listen and learn, we also marvel at the fact that in this vast cosmos, light that began its journey billions of years ago can still reach us, carrying with it the secrets of stars that lived and died long before our Earth even formed. Cosmic strings are one of the most fascinating and mysterious ideas ever proposed in the study of the universe. They belong not to the world we see every day with our eyes and hands, but to the deeper hidden layer of reality, where the fabric of space and time itself may contain strange imperfections. To imagine them, one must first think of the universe not as empty, airless space dotted with stars and galaxies, but as a kind of immense and delicate tapestry, woven together from invisible threads. In this grand cosmic tapestry, most of the fabric appears smooth and continuous, but perhaps at certain places there are seams, lines, or wrinkles. These irregularities are not ordinary cracks or tears, but defects at the most fundamental level of existence. Out of these possible flaws in the cosmic weave emerges the idea of the cosmic string. A cosmic string, if it exists, would not be like any physical object that people are used to. It would not resemble a metal wire, a rope, or even a hair. Instead, it would be an unimaginably thin, one-dimensional thread stretching across vast distances in the universe. In fact, in theory, such a string could be millions of light-years long, yet so narrow that it would make even the thinnest fibre known to humans look enormous by comparison. Though unimaginably thin, the density of energy packed into this thread would be so extreme that it could outweigh a mountain in just a fragment of a strand. To our ordinary senses, it would be invisible and untouchable, but in its interaction with space itself, it would be powerful enough to bend the paths of stars and even the motion of light. The idea of cosmic strings comes from the earliest days of the universe, moments after the great beginning known as the Big Bang. At that time, nearly 14 billion years ago, the cosmos was in a state of wild transformation. In a fraction of a second, the universe grew from something smaller than an atom to a vast expanding sea of energy and matter. This explosive swelling is known as cosmic inflation. During that brief but all-important phase, the universe cooled and settled, and as it did, some regions may not have smoothed out perfectly. Instead, defects could have been left behind, etched into space itself like frozen scars. Cosmic strings are one possible kind of defect that might have survived from those earliest moments, carrying with them clues about the laws of nature at energies far greater than anything we can recreate in laboratories on Earth. The comparison most often used is with phase transitions. Just as water turning into ice can trap air bubbles or create cracks in the crystals, the universe going through its own changes of state may have left behind imperfections in the field that governs the forces of nature. These imperfections are what physicists call topological defects. A cosmic string would be such a defect, not in matter itself, but in the structure of space-time. Topology, the mathematical field that studies how shapes behave under stretching, bending, or twisting, tells us that such defects can exist in certain systems. If space-time is a kind of shape, then cosmic strings are the frozen wrinkles in it. But these strings are not passive relics just lying quietly across the cosmos. They would be dynamic, restless, and capable of motion. Imagine a tight violin string vibrating when plucked, except here the string is not wood or metal, but the very geometry of space. These cosmic strings would oscillate, twist, and sometimes even loop back on themselves. Their vibrations would not create sound, but something far more profound, ripples in the very fabric of space-time. These ripples are gravitational waves travelling outward at the speed of light. Unlike the gravitational waves detected in recent years from colliding black holes or merging neutron stars, which are the aftershocks of massive astrophysical objects, the waves from cosmic strings would arise from the very structure of the universe itself. Physicists have long speculated about these possible signals. If a cosmic string loop formed, it could wiggle and whip around, creating sharp bursts of gravitational energy. Some theorists believe that special points on these oscillating strings, called cusps, could accelerate parts of the string to nearly the speed of light, producing intense flashes of gravitational radiation. These bursts might travel across the universe and, in principle, could be detected by the most sensitive instruments designed to listen to spacetime's vibrations. The dream is that one day, observatories like LIGO or future detectors in space could catch one of these signals, offering proof that cosmic strings are real. But for now, this remains a hope, for no evidence has yet appeared. If such waves exist, they are faint, subtle, and difficult to separate from the cosmic background noise. The energy locked within cosmic strings would be extraordinary. Because of their immense tension and their ultra-thin but extremely dense nature, they would contain power beyond imagination. If two strings crossed paths, they could reconnect, snapping and rejoining in different configurations. When this happens, loops of string could break off and shrink, radiating away their energy in powerful gravitational bursts. Some have even suggested that cosmic strings could be responsible for strange high-energy events in the universe that we do not yet fully understand. Could they be behind some mysterious cosmic rays, or unusual gravitational signals that occasionally puzzle astronomers? No one knows, but the speculation is tempting. Now imagine the dramatic consequences if a cosmic string were to drift near a massive object, like a star or even a black hole. The presence of the string would warp the surrounding spacetime. Light from background stars could be bent into unusual shapes, creating distinctive lensing patterns. Planets might feel a sudden tug, shifting their orbits. On even larger scales, entire galaxies could be influenced by the gravitational effects of these hidden lines. Some models suggest that during the early history of the cosmos, the presence of strings might have played a role in the way matter gathered together, helping to seed the formation of galaxies and galaxy clusters. The idea that the invisible threads of cosmic strings might have helped weave the structure of the visible universe is one of the most poetic suggestions in modern physics. One of the strangest and most beautiful aspects of this theory is its connection to the deepest questions about reality. Cosmic strings are not just wild guesses, they are natural consequences of certain theories that attempt to unify the forces of nature. In the world of particle physics, where scientists search for the single framework that ties together electromagnetism, the nuclear forces and gravity, strings appear as unavoidable mathematical results. They are hints that the universe may contain layers of reality far beyond what humans can currently test. Thus, even though no cosmic string has ever been observed, the pursuit of them continues, because their discovery would immediately confirm that our understanding of the universe's infancy and its deepest laws is on the right track. If one day we do find cosmic strings, the breakthrough would rival some of the greatest scientific discoveries in history. Just as Albert Einstein's prediction of gravitational waves took a full century to be confirmed, so too might the search for strings require generations of patient observation. Yet the reward would be immense. It would mean that we have touched, however briefly, the scars of creation itself. These thin, invisible highways of energy would be fossils from the dawn of time, preserving information about conditions that no telescope could otherwise reveal. It is important to emphasize just how alien such objects would be. They are not made of atoms, molecules, or any material substance. They are features of space itself, like creases in a sheet. They are one-dimensional in the strictest sense, having length but essentially no thickness. If one were to pass through Earth, we would not see it, but the planet might feel a sudden jolt as its gravitational influence pulled matter slightly off balance. Over cosmic distances, their cumulative effect could be enormous, yet locally they would be nearly impossible to detect except through the gravitational waves they emit, or the lensing patterns they create. Some visionaries even describe cosmic strings as energy highways, for in theory, they could channel vast amounts of energy through their oscillations. If advanced civilizations ever existed in the far future of the cosmos, they might dream of harnessing such energy. For now, this belongs more to the realm of science fiction than science fact, but it captures the sense of awe that the concept inspires. The thought that the universe itself may hide such threads, humming and vibrating across billions of light years, is a reminder of how much remains unknown. The study of cosmic strings ties together physics, mathematics, cosmology, and imagination in a way that few other ideas can. Dark matter annihilation is one of the most fascinating and mysterious ideas in all of modern science, an idea that blends the invisible forces of the cosmos with the possibility of hidden power sources that could shape the destiny of galaxies and perhaps the fate of the universe itself. To understand this concept, one must first appreciate the strange and uneven balance of matter and energy that makes up reality as we know it. When astronomers carefully weigh the universe, counting all the stars, gas, dust, and visible galaxies, they find that ordinary matter, the kind of matter that makes up you, me, the earth beneath our feet, the sun shining in the sky, and even the most distant stars twinkling billions of light years away, is only a tiny fraction of the whole. Ordinary matter, also known as baryonic matter, accounts for only about 5% of the entire cosmic inventory. Much more abundant than ordinary matter is dark matter, which contributes roughly 27% of the total mass and energy of the universe. The remainder, a staggering 68%, is something even stranger still: dark energy, the invisible pressure that is causing the universe to expand at an ever-accelerating rate. If the cosmos were a great recipe, ordinary matter would be only a small pinch of seasoning, while dark matter and dark energy would make up almost the entire meal. Yet despite their overwhelming dominance, these dark ingredients remain hidden from our direct senses. No telescope can take a picture of dark matter. No spectroscope can split its light into colours, for it emits no light at all. It is a silent, invisible ghost that reveals itself only through the pull of its gravity, and perhaps through faint whispers of other interactions too weak to notice directly. This mystery raises one of the greatest questions of science. What is dark matter actually made of? One theory suggests that it consists of particles, not unlike the particles that make up atoms and molecules, but belonging to a hidden realm of physics beyond the familiar standard model of particle physics. If this is true, then these dark matter particles might sometimes collide with one another, and when they do, the result could be astonishing. Just as matter and antimatter annihilate when they meet, releasing pure energy, so too might dark matter particles annihilate when they crash together, releasing their hidden energy in bursts of radiation, such as gamma rays or other high-energy particles. This process is called dark matter annihilation, and if it truly happens, it might leave behind signals that we, the watchers of the cosmos, could detect. Imagine the universe filled with invisible particles constantly streaming through space, silent and unseen. Most of the time they pass through one another without effect, for their interactions are faint and elusive. But occasionally in the densest regions of the cosmos, two such particles collide. In that fleeting instant their mass vanishes, converted entirely into energy, just as Einstein's famous equation foretells. A flash of gamma rays, among the most energetic forms of light, is born and races outward at the speed of light, travelling vast distances across the gulfs of interstellar space. Gamma rays are particularly valuable to astronomers because they are so hardy. Unlike visible light, which can be scattered or absorbed by dust, or radio waves, which can be distorted, gamma rays fly across the universe largely untouched, carrying the unspoiled signature of the violent events that created them. They are like incorruptible messengers, whispering secrets from the farthest corners of existence. If dark matter annihilation is real, and if it happens often enough, then somewhere out there the sky's sprinkled with these hidden messages, waiting for us to decode them. That is why scientists have built sensitive gamma-ray telescopes and pointed them at promising regions of the sky, searching for unusual patterns of radiation that cannot be explained by ordinary stars, supernovae, or black holes. The most promising of all targets is the very heart of our own galaxy, the Milky Way. For if dark matter is everywhere, it should be densest at the galactic centre, where gravity has gathered matter together in its deepest well. In that crowded core where stars swarm like bees and black holes prowl, there should also be a concentrated sea of dark matter particles, drifting and colliding from time to time. If annihilation happens anywhere, it should be most visible there. Indeed, astronomers have discovered something curious. From the centre of the Milky Way, they observe a strange, diffuse glow of gamma rays that does not match any known source. This glow is not shaped like the emissions of pulsars, nor does it resemble the remnants of exploding stars. It does not quite fit the models of cosmic rays interacting with gas and dust. Instead, it has certain features that make it eerily similar to what some physicists would expect if dark matter particles were colliding and annihilating in that region. To some, this glow is the long-sought clue, the whisper of dark matter finally revealing itself. But science is cautious. Many researchers warn that there are other possible explanations. Pulsars, the rapidly spinning remnants of dead stars, can also emit gamma rays. Cosmic rays crashing into interstellar gas could mimic the signal. The galactic centre is a busy and chaotic place, filled with so many energetic phenomena that disentangling them is like trying to hear a whisper at the heart of a roaring crowd. What seems like dark matter's signature may turn out to be a trick of the background noise, a mirage of astrophysical processes. Thus the debate continues and the mystery deepens. While gamma-ray searches continue, scientists are also trying other strategies. On Earth, in deep underground laboratories shielded from cosmic radiation by mountains of rock, detectors are set up in hopes of directly catching a dark matter particle in the act of interacting with ordinary matter. These detectors are built with exquisite sensitivity, designed to notice even the faintest nudge of a dark particle brushing against an atom. But so far, despite years of effort, no clear detection has been made. The silence persists, deepening the enigma. Even so, hope remains, because the stakes are enormous. If scientists can one day confirm that dark matter particles truly annihilate and produce detectable signals, it would not only prove that dark matter exists, which itself would be one of the greatest discoveries of modern physics, but it would also open the gateway to entirely new physics beyond the standard model. The very properties of dark matter, its mass, its behavior, its annihilation channels, would provide a treasure trove of information about the hidden forces of the universe. It would be like opening a new book of nature, filled with chapters we never knew existed. The implications would stretch far beyond particle physics. Dark matter, after all, is the scaffolding of the cosmos. Galaxies formed within its gravitational embrace, stars lit up where dark matter gathered. The cosmic web that binds the universe is woven from its threads. If we understood how dark matter behaves, how it annihilates, how it interacts, we could better explain why galaxies have the shapes they do, why clusters of galaxies arrange themselves across the universe in a vast lacy network, and perhaps even how the future of the cosmos will unfold. Dark matter annihilation might not only be a source of hidden energy, but also a guiding hand in the grand story of cosmic evolution. It is thrilling to imagine that dark matter annihilation might even influence star formation. If annihilation releases enough energy in dense regions, it could warm surrounding gas clouds, changing how stars ignite. In the early universe, when galaxies were first forming, such annihilation could have added a secret energy budget, a hidden glow shaping the pace of creation. In the far reaches of cosmic time, perhaps it still does. The possibility that invisible collisions of unknown particles could regulate the life cycles of galaxies gives the universe a sense of secret design, a hidden script we're only beginning to decipher. The search for dark matter annihilation is therefore not just a technical pursuit, but a profound quest. It asks us to look into the shadows of existence, to listen for the faintest echoes of invisible events, and to imagine a reality richer and stranger than anything our senses can directly perceive. It demands patience, for the signals are faint and the interpretations tricky. It demands courage, for the answers may force us to rewrite the foundations of physics. And it demands wonder, for in chasing the ghostly glow of annihilation, we are truly seeking to understand what the universe is made of and how it came to be. Perhaps one day the gamma-ray telescopes will find an unmistakable signal, a fingerprint of dark matter that cannot be denied. Perhaps a particle detector buried deep beneath the Earth will at last feel the touch of a dark particle and shout its discovery to the world. Perhaps a new theory, bold and elegant, will explain not only what dark matter is, but also why it annihilates and how it has shaped everything we see. When that day comes, humanity will have taken one of the greatest steps in its long journey of knowledge. We will have lifted a corner of the cosmic veil and glimpsed the hidden machinery of creation. Until then, the search goes on, a grand adventure into the invisible powered by curiosity and imagination, guided by the faint glow of annihilation's promise. Imagine a crash so enormous that it makes even the most powerful explosions in the universe look small by comparison. That is what happens when two galaxy clusters collide. These events are not ordinary in any sense. They are cosmic spectacles of unimaginable size and energy, involving entire swarms of galaxies, rivers of blazing hot gas, and invisible oceans of dark matter. To witness such a collision, even from afar, is to see one of the universe's most breathtaking and violent performances. A galaxy cluster is not just a single galaxy. It is a gathering of thousands, sometimes even tens of thousands, of galaxies bound together by gravity. Each galaxy in turn may hold billions or even trillions of stars, along with planets, nebulae, and black holes. These clusters are the largest structures in the universe that are held together by their own gravity, stretching across many millions of light years. Now imagine two such titanic collections of galaxies moving toward each other over cosmic timescales. Their meeting is not a simple brushing of shoulders, it is a clash that shakes the very fabric of space itself. When clusters collide, the event unfolds on a stage measured not in miles or kilometers, but in light years. The scale is so immense that even though stars themselves almost never hit one another, because the distances between stars inside galaxies are like vast oceans of emptiness, their surrounding environments do interact in dramatic ways. The key players in these crashes are not just the galaxies themselves, but the colossal clouds of gas that fill the space between them. These gas clouds are not gentle or cool. They are furnaces of energy, heated to tens of millions of degrees, glowing fiercely in the X-ray part of the spectrum. When clusters come together, these gas clouds slam into each other at tremendous speeds. The result is a compression so violent that it raises their temperatures even higher, sometimes reaching up to 100 million degrees Celsius or more. At those temperatures, the gas becomes an almost unimaginable cauldron, blazing with radiation. It is like smashing two giant oceans of fire together and watching the shockwaves ripple across space. The galaxies, as mentioned, often drift past one another largely untouched, like two flocks of birds flying through each other without colliding. But the gas cannot avoid direct contact. It collides, crashes, and roars with turbulence. This produces shockwaves that sweep through the cluster, not unlike the sonic booms that jets make when they break the sound barrier. These cosmic shockwaves carry enough energy to make the cluster blaze brighter than all its stars combined. In the aftermath, the gas becomes a stormy sea, with whirlpools of turbulence twisting and stirring the cluster into a chaotic mess. Yet there is more to these collisions than just visible fireworks. Hidden in the background is the mysterious force of dark matter. Dark matter does not shine, does not glow, and does not emit any form of light that we can see, and yet it makes up most of the mass in these clusters. When galaxy clusters crash into each other, their dark matter halos, vast invisible envelopes of mass, pass through one another almost as if nothing happened. Unlike the gas, which collides and slows down, dark matter drifts smoothly on, guided only by gravity. This curious behaviour allows astronomers to study dark matter in ways no laboratory experiment on Earth could achieve. By observing how the visible gas and galaxies separate from the invisible halos of dark matter during collisions, scientists get powerful clues about the properties of this ghostly substance. One of the most famous examples is what astronomers call the bullet cluster. In this extraordinary system, two galaxy clusters collided at immense speed. The visible clouds of gas smashed together and slowed down, piling up like the crumpled hood of a car after a crash. But the dark matter passed through unaffected, leaving it offset from the visible matter. This separation created a natural cosmic experiment, showing clear evidence that dark matter exists and behaves differently from ordinary matter. But galaxy cluster collisions are not just spectacular cosmic accidents, they are also engines of change in the universe. When the shockwaves from the crash ripple through the hot gas, they can push material together, creating regions dense enough for new stars to form. This process, known as a starburst, can ignite the birth of thousands of stars in a relatively short cosmic time. Whole generations of suns can be triggered into existence by the violence of these events. At the same time, collisions can also smother star formation. If the gas is heated too much or stirred up too violently, it can no longer cool and collapse into stars. In this way, a galaxy cluster collision can both spark and suppress star birth, shaping the destiny of galaxies within it. Some regions may blaze with newborn stars, while others may go dark and quiet. Their ability to create new stars shut off for billions of years. The energy unleashed is staggering. The X-rays and other radiation pouring out of a collision can ripple outward for millions of light years, influencing not just the colliding clusters, but even nearby structures. Over billions of years, these cosmic rumbles help shape the way galaxies and clusters arrange themselves across the universe. Each collision is like a hammer strike on the cosmic drum, sending vibrations across the great web of galaxies that threads through space. For astronomers, watching these collisions is like peering into the universe's instruction manual. By studying them, scientists can learn how galaxies grow, how dark matter behaves, how cosmic structures evolve, and perhaps even how the universe itself will change in the far future. Telescopes that detect X-rays, radio waves, and even gravitational effects are used to capture these events in detail. The information gathered is then fed into computer simulations that attempt to recreate the crash. These simulations are like time machines, allowing astronomers to slow down and replay events that in reality unfold over billions of years. By comparing simulations to real observations, scientists can refine their understanding of physics on the grandest scales imaginable. The story of galaxy cluster collisions is therefore one of both destruction and creation. They are wrecking balls of the cosmos, smashing gas and shaking galaxies, yet at the same time they are cosmic forges, sparking new stars and reshaping the universe. They reveal the presence of dark matter, show us the power of shockwaves, and remind us of the staggering scale of cosmic forces. When we look at a picture of the bullet cluster, or any other colliding clusters, we are not just seeing distant galaxies. We are witnessing the clash of giants, battles fought over millions of light years, echoing across billions of years of time. These colossal cosmic rammers remind us that the universe is alive with motion, growth, and energy, and that even the largest structures are not static but constantly changing through encounters as dramatic as anything we can imagine. Gravastars and other strange compact cosmic objects are some of the most fascinating what-ifs of modern astrophysics. For a long time, black holes have been the main explanation for the most extreme places in the universe where gravity rules with unstoppable power. They are the champions of cosmic collapse, the final stage in the life of the heavier stars. Yet, the idea of a gravastar suggests that the story of dying stars might not always end in the way we have been told. It introduces the possibility of something even stranger, a kind of compact object that does not behave exactly like a black hole, but still has almost impossible density and gravitational strength. The well-known tale goes like this. A massive star burns through its nuclear fuel over millions of years. When the fuel is gone, the star can no longer fight against its own gravity. Its core collapses inward, shrinking under the weight of its own mass. In most scenarios, this collapse continues until it forms a black hole, a region where gravity becomes so strong that nothing, not even light, can escape. But the Gravastar changes this story. It suggests that the collapse might not always reach the point where gravity becomes infinite. Instead, it might stop just short of forming a true black hole. At this point, the star could stabilize in a very unusual state, creating what scientists describe as a kind of vacuum bubble at its center. The idea of a gravastar is not based only on gravity, but also on the strange rules of quantum mechanics and exotic states of matter. Normally, we imagine matter being squeezed tighter and tighter until it has no choice but to collapse further. But in the Gravastar model, quantum forces step in before the collapse reaches infinity. These forces act as a kind of pressure that halts the process. The result is a compact shell of ultra-dense matter surrounding an empty bubble-like center. This hollow core is not filled with ordinary matter, but with a region of extremely low density, a kind of vacuum where the strange effects of quantum physics dominate. This structure makes the Gravastar an odd twin of the black hole. Both are incredibly compact and both bend light and space around them. But the Gravastar is not a true singularity. Instead of everything being crushed into a single point of infinite density, its outer shell creates a boundary where exotic matter and energy interact in mysterious ways. This shell is thought to be held together by forces so powerful that they prevent it from collapsing further. Unlike the event horizon of a black hole, which is the ultimate point of no return, the boundary of a Gravastar is not absolute. Light and information might still be able to escape from it, making it different in a subtle but crucial way. Inside a Gravastar, things become even stranger. Some theoretical models suggest that exotic forms of energy or particles could exist there, perhaps even something like dark energy or unknown quantum fields. These would be packed tightly within the outer shell, creating a delicate balance between the crushing pull of gravity and the mysterious push of quantum pressure. If this balance is real, it would mean that Gravastars could survive as stable cosmic objects instead of collapsing further into black holes. This idea also offers a solution to one of the most puzzling mysteries of black holes, the singularity. In the classic black hole model, anything that crosses the event horizon is doomed to end up at the singularity, a point of infinite density where the known laws of physics break down completely. Gravastars present a different possibility. They suggest that matter may never reach infinite density at all. Instead, it would end up in a strange state of matter compressed to unimaginable levels but still balanced, avoiding the paradox of infinity. From far away, a Gravastar would look almost identical to a black hole. Both would be small in size compared to their mass. Both would bend light so severely that they could act like cosmic magnifying glasses through gravitational lensing, and both would create swirling disks of matter as gas and dust fell toward them. Observing one from Earth would make it nearly impossible to tell which was which. The big difference lies in what happens at their boundaries and in their interiors. A black hole traps everything inside forever. A Gravastar, on the other hand, might let some light and information escape, offering a tiny window into what lies within. Gravastars are not the only exotic alternatives to black holes. Another strange idea comes from string theory and is known as the fuzzball model. According to this view, what we call a black hole might not contain a singularity at all. Instead, it could be a giant tangled ball of microscopic strings, the building blocks of reality and string theory. This fuzzball would spread out over a large region, replacing the infinitely small point of a singularity with a far more complicated structure. From the outside, it would look almost the same as a black hole, creating the same gravitational effects, but inside it would be an enormous web of quantum threads. Both Gravastars and fuzzballs challenge the traditional view of black holes and force scientists to reconsider how the universe really works. If either of them exists, they would change our understanding of the fate of stars, the nature of matter, and even the structure of space-time itself. At present, however, these ideas remain unproven. So far, every major observation has supported the traditional picture of black holes. We have detected gravitational waves from black hole collisions, and we have even captured the first image of the shadow of a supermassive black hole in the galaxy Messier 87. These findings continue to strengthen the classic black hole model, and yet the possibility of Gravastars and fuzzballs lingers, reminding us that science thrives on questions as much as on answers. Among all the unsettling and mind-bending ideas that modern physics has given us, few are as haunting as the concept of vacuum decay. At first glance, the universe feels permanent, solid, and trustworthy. The stars have shone for billions of years, the galaxies wheel across the heavens, and the laws of nature seem dependable and unchanging. Yet this idea tells us that the very stage upon which everything exists, the vacuum itself, the apparent emptiness of space, might not be as stable as we think. Hidden beneath the calm and silence of the cosmos, there may be the possibility of a sudden and absolute disaster that would not simply destroy planets or stars, but would erase the very framework of reality. The theory is strange but chilling. It suggests that a bubble could form somewhere in the universe. A bubble not filled with gas or matter, but with a new kind of vacuum, a true vacuum. Within this bubble, the laws of physics would not be the ones we know. They would be rewritten in ways we cannot predict. And if such a bubble appeared, it would not just sit still. It would grow at almost the speed of a light, swallowing everything in its path. Stars, galaxies, atoms, space itself, and even time. Nothing could withstand it. To understand why scientists even imagine such a possibility, we must look at the strange world of quantum physics. The vacuum of space, the black background that looks like nothing, is not truly empty. According to quantum field theory, space is alive with restless activity. Particles and their opposites, called antiparticles, are constantly flickering into existence and then disappearing again, as if the universe is never quite at rest. This restless ocean of tiny events is called vacuum fluctuation. Out of this seething sea comes the idea that the vacuum might not be in its lowest, most stable state of energy. Instead, it may be stuck in what physicists call a false vacuum, a temporary state that only looks stable but is not the deepest possible foundation. Imagine the universe as a ball resting in a shallow hollow on the side of a hill. To us it looks stable, but just beyond lies a deeper valley. If the ball were to slip into that deeper valley, it would roll down to a state of lower energy, a true vacuum. If the universe made such a transition, the consequences would be absolute and unstoppable. Everything that depends on the current laws of physics, every particle, every force, every constant, would be rewritten. Gravity might not pull the same way, light might not move at the same speed, atoms themselves might not hold together. In an instant, all familiar structures would vanish. Quantum mechanics provides the eerie mechanism by which this could happen. In the quantum world, particles do not behave like solid marbles bound by rigid walls. Instead, they sometimes tunnel through barriers that should be impossible to cross. A particle that cannot climb over a wall in classical physics might simply appear on the other side in quantum physics. This strange trick of tunneling makes it possible for the universe itself to slip from the false vacuum into the true vacuum. The bubble of true vacuum would form, and once it began, it would expand relentlessly, erasing everything it touched. What makes this possibility uniquely horrifying is that it is unlike any other cosmic disaster we can imagine. A supernova, no matter how violent, still follows the laws of physics we know. The collision of black holes, though cataclysmic, still operates within familiar rules. But vacuum decay is not just another disaster, it is the annihilation of the rules themselves. The collapse of space-time, the disintegration of all forces and particles would mean not even the idea of survival or rebuilding would make sense. There would be no observers left, no records, no memory, no possibility of escape, and worst of all, if such a bubble were to appear, we would never see it coming. Since it would move at nearly the speed of light, there would be no warning. One instant, the stars would shine and life would go on as always. The next instant, everything would be gone, rewritten into something utterly alien. No spaceship, no technology, no advanced civilization, no matter how powerful, could outrun it. The expansion would be unstoppable, like a tide sweeping across the entire cosmos. It is hard to imagine a catastrophe greater than this. Stars, planets, and galaxies, all swallowed by a wave that changes not only matter, but the very essence of existence. Time itself would be undone. The universe would be reset in a way so radical that nothing recognizable would remain. But before we sink into despair, it is important to remember, this terrifying scenario is, for now, entirely theoretical. Physicists have worked out the mathematics of vacuum decay, and it fits consistently within the frameworks of quantum field theory. Yet there is no evidence that such an event is happening, or even likely to happen anytime soon. The energy levels required for such a transition are staggeringly high, so high that the universe, as far as we know, is not close to reaching them. Many scientists believe we are safe, at least for now. Some even argue that the universe might already be in the true vacuum state, and that the false vacuum idea does not apply at all. Still, the possibility raises unsettling questions. If our current universe is only a false vacuum, then what does stability really mean? Could the constants of nature, like the strength of gravity, or the electric charge of particles, suddenly shift to entirely new values? If everything we take for granted rests on a foundation that might not be permanent, how much of our reality is just a temporary illusion? In the traditional story of the Big Bang, scientists believe that in the very first blink of creation, the universe expanded at a speed so fast it is almost beyond comprehension. This event, called inflation, took place in the tiniest fraction of a second after the Big Bang. It stretched the newborn universe outward faster than light itself, smoothing out irregularities and scattering energy and matter across space. That rapid growth set the stage for the later birth of galaxies, stars, and planets, including the world we now live on. But there is a more daring idea, one that goes even further than this original inflation story. It is called eternal inflation. While traditional inflation says that the rapid expansion slowed and eventually stopped everywhere, eternal inflation suggests something far stranger. Inflation never ended all at once. Instead, it continued endlessly in some regions, creating a never-ending cascade of bubble-like universes. Each of these universes is its own self-contained cosmos, with its own rules, its own laws of physics, and perhaps even constants of nature that are not the same as those we know in our universe. To picture this, imagine the universe not as a single bubble, but as an endless foam of bubbles. Our own cosmos is just one bubble among countless others. In between these bubbles lies space that is still inflating forever, driven by an incredibly powerful field of energy known as the inflaton field. This field acts like an engine, pushing the expansion forward without end, and in doing so, it separates one bubble universe from another. Together, all of these bubbles form what scientists call the multiverse, an unimaginably vast collection of universes, each potentially unlike any other. If eternal inflation is real, then our universe is not unique at all. Instead, it is only one among an infinite sea of possibilities. Most of these universes would be forever unreachable. They are so far away and so isolated by continuing inflation that no signal, no traveller, and no technology could ever bridge the distance. They are causally disconnected, meaning that nothing from one bubble can ever affect another. Each universe lives in its own private reality, cut off from the rest. Inside these bubbles, conditions vary wildly. One bubble might contain a universe where gravity is stronger or weaker than in ours. Another might have light travelling at a different speed. Some universes may be bursting with matter, stars, and galaxies, while others could be almost entirely empty, vast voids without a single atom. Some might have temperatures, energies, and forces that make life possible, while others may be cold, dark, and forever barren. This endless variation means that the multiverse could contain every kind of universe imaginable, from ones almost identical to ours to ones that are utterly alien. This idea also helps explain puzzles about our own cosmos. For example, why is our universe so smooth and uniform when we look at it on the larger scales? Across billions of light years, the cosmic microwave background radiation, the faint afterglow of the Big Bang, shows nearly the same temperature everywhere. This is surprising, because regions of space that far apart should never have been able to share information or heat with one another. Inflation provides an answer. That early burst of rapid expansion allowed distant regions to have once been close enough to mix, and even out before being pushed apart. Eternal inflation suggests that this kind of smoothing effect might be happening again and again in bubble after bubble across the multiverse. But then comes the deeper question. What does it mean if our universe is just one bubble among an infinite number? In some of those other bubbles, perhaps life arises as it has here. In others, life might be utterly impossible, the laws of physics so strange that atoms cannot even hold together. There may even be bubbles that resemble ours in uncanny ways, with universes where events play out in familiar but slightly altered forms. The thought stretches the human imagination, challenging us to rethink reality itself. The problem, of course, is proof. If these other universes are forever out of reach, how can we ever know they exist? Direct observation seems impossible because the barriers between bubbles are endless expanses of inflating space. Some scientists suggest that faint traces of eternal inflation might be hidden in the cosmic microwave background radiation, perhaps as unusual patterns left behind by the collision of bubbles long ago. If such patterns could be found, they would offer indirect evidence of the multiverse. But detecting such faint whispers in the sky is almost unimaginably difficult, and even then, it would not be a guarantee. For now, eternal inflation is a bold idea supported by mathematical models and theories rather than by hard evidence. Still, this idea has tremendous power. It forces us to ask questions that reach to the very edge of understanding. If the multiverse is real, then reality is not limited to the single universe we see. Instead, existence is far broader, stranger, and more varied than we ever imagined. The nature of space, time, and reality itself may be richer than anything we can grasp. Even if we never observe another bubble universe directly, the possibility that they exist reshapes the way we think about the cosmos and our place in it. The more scientists learn about the universe, the clearer it becomes that we are only beginning to scratch the surface of a much deeper mystery. Eternal inflation is one of the grandest ideas yet, one that stretches both the limits of physics and the human imagination. Whether or not it turns out to be true, it invites us to dream bigger, to consider the possibility that we live not in the only universe, but in a vast and endless sea of universes, an eternal multiverse without beginning or end. In the vastness of the universe, most of what we observe appears to be governed by immense gravitational forces and cataclysmic explosions. Stars are born and die in blazing furnaces, black holes consume everything around them, and galaxies collide over billions of years. Yet beyond these familiar cosmic dramas, there exists a fascinating and speculative realm where energy and information are not separate entities, but intertwined in ways that challenge our deepest intuitions. This domain suggests that the very building blocks of reality might one day be shaped not only to store and transmit energy, but to process information with unparalleled efficiency. At the center of this idea is a concept called Computronium, a theoretical form of matter that is optimized for computation itself. Computronium represents more than just super-powerful computers. It is a substance in which the material itself, at the atomic and subatomic scale, is designed to carry out calculations, store data, and manipulate information with incredible efficiency. In this sense, the very structure of matter is repurposed for the processing of information. While today our most advanced computers are composed of silicon chips and complex circuits, in a universe where Computronium exists, the lines between physical material and computational capability blur entirely. The cosmos itself could, in principle, become a vast network of information processing, each fragment of matter potentially engaged in operations beyond our present understanding. The concept of Computronium collisions extends this speculation into an even more extraordinary domain. If regions of Computronium were to interact or collide, especially under conditions of extreme velocity or energy, the results could transcend conventional physics as we know it. Unlike traditional collisions of matter, which release energy primarily through chemical reactions or nuclear processes, The collision of Computronium would release energy directly tied to the flow of information within the material. The disruption of these computational structures would not only destroy data, but convert the act of information processing itself into a new form of energy release. To better understand this, consider the familiar example of nuclear reactions, such as nuclear fission, where the energy stored in the binding forces of atomic nuclei is unleashed when the nuclei split apart. Similarly, fusion combines light nuclei to produce heavier elements and enormous amounts of energy. Computronium collisions operate on an analogous principle, but at the level of information rather than simple atomic mass. The energy released would be a direct consequence of the disturbance of highly organized computational structures. These collisions could generate bursts of radiation and energetic particles unlike anything naturally occurring, a phenomenon arising from the destruction of information itself rather than the simple rearrangement of matter. The potential scale of such events is staggering. If vast regions of Computronium existed, particularly those developed or maintained by advanced civilizations, the energy released from even small collisions could be immense. Shockwaves might propagate not just through physical space but through networks of computational information, creating cascading effects across enormous distances. The event would be as complex as a supernova or a black hole merger, yet fundamentally different in its origin. Instead of energy stemming from gravitational collapse or nuclear fusion, it would originate from the intrinsic computational processes embedded within matter itself. In this way, Computronium collisions might redefine our very understanding of energy, bridging the conceptual gap between physics and information theory in a manner unprecedented in known science. The implications for advanced civilizations are profound. A species capable of creating and controlling Computronium could harness energy directly from computational processes, potentially on a scale comparable to stars. They might design massive constructs in which information processing and energy production are inseparable, creating systems where every calculation contributes directly to the generation of usable energy. Such civilizations could manipulate reality itself, using Computronium networks to conduct simulations of entire universes or to guide cosmic-scale engineering projects. Interstellar collisions of these networks could be both a source of power and a tool for understanding and controlling the universe in ways currently inconceivable. Beyond the concept of Computronium lies an even more abstract idea: causality engines. These hypothetical devices take the relationship between energy and information a step further, proposing that the very flow of time could be harnessed as a resource. Unlike conventional machines that rely on matter, fuel, or electromagnetic energy, causality engines would exploit time gradients, the natural variations in how time passes across different regions of space. According to Einstein's theory of relativity, time is not uniform. It flows differently depending on the strength of gravitational fields or the velocity of objects. Clocks on satellites in orbit tick slightly differently than those on Earth due to gravitational differences, an effect confirmed experimentally many times. If such differences in time flow could be harnessed, they could potentially be converted into usable energy. A causality engine operates conceptually like a heat engine, but substitutes time for temperature. A traditional heat engine draws energy from a hot reservoir, performs work, and dissipates the remaining heat into a cooler reservoir. In an analogous manner, a causality engine would exploit the differences in the passage of time across two regions. By channeling energy from areas where time flows faster to areas where it flows slower, the device could convert temporal gradients into mechanical or electrical energy. The very act of time's unequal passage becomes a source of work. The engineering challenges of such devices are immense. Time gradients exist naturally near massive objects like black holes, but artificially creating and controlling them would require a level of technology far beyond current human capabilities. It would not simply involve producing a gravitational field, but manipulating space-time itself to create controlled regions with predictable differences in temporal flow. The energy necessary to achieve such effects would likely surpass even the most powerful energies humanity has ever produced, placing causality engines at the edge of speculative physics. The implications of harnessing temporal energy are both thrilling and daunting. A civilization capable of building causality engines could construct environments where time flows differently internally than externally. In principle, a spacecraft could have regions in which time passes more slowly than in the surrounding universe, allowing it to generate energy or conduct computations at rates far beyond what would be possible otherwise. By exploiting time gradients, such a ship could harness energy directly from the structure of space-time, bypassing conventional fuel or material limitations. The engines could enable propulsion methods or energy production that seem impossible according to the laws of physics as currently applied to mass and energy alone. However, manipulating time comes with significant risks. Altering the flow of time, even locally, could produce unpredictable effects, potentially destabilizing causality. Events that should follow a logical sequence might be disrupted, and paradoxes could emerge. Large-scale temporal manipulation might even distort the fabric of space-time, creating regions where past, present, and future blur together. The consequences of such manipulations are fundamentally unknowable, raising questions about whether time itself could be depleted, damaged, or distorted in a way that undermines the stability of the universe. Returning to Computronium, the marriage of high-energy physics and computational theory, represented by these collisions, is both a scientific and philosophical exploration. It asks whether information itself is a form of matter, whether the processing of data can generate tangible energy, and whether advanced civilizations could exploit these principles to a degree that transforms the cosmos. Just as the discovery of nuclear energy revolutionized humanity's understanding of matter, the realization of Computronium-based energy could revolutionize our understanding of information, energy, and the fundamental architecture of reality. The universe might contain regions of matter so optimized for computation that their interactions release energy not by conventional means, but through the disruption of highly organized information networks. These events could produce waves of radiation, particles, and computational anomalies propagating through space. Advanced civilizations could orchestrate such collisions to generate power or simulate entire universes at a scale that dwarfs anything imaginable today. The energy extracted would not be merely thermal or kinetic, but fundamentally informational, turning the fabric of reality into a source of usable power. While humans remain far from creating Computronium or harnessing temporal energy, the theoretical exploration of these concepts pushes the boundaries of physics, cosmology, and philosophy. By considering matter optimized for computation and time as a resource, scientists and theorists challenge conventional notions of energy, work, and reality itself. In these speculative domains, intelligence, matter, energy, and time are not separate entities, but part of an interconnected system where the manipulation of one aspect can influence all others. In summary, Computronium represents a theoretical form of matter designed to process information at an unprecedented level, where collisions between such matter could release energy through the destruction of information itself. This concept extends the boundaries of traditional physics, suggesting that energy need not be tied solely to mass, gravity, or nuclear forces. Likewise, causality engines offer a vision in which time itself becomes a usable resource, capable of being converted into energy through differences in temporal flow. Together, these ideas hint at the possibility of a universe where information, energy, and time are interwoven, and where advanced civilizations could operate on scales and with principles that are profoundly alien to our current understanding. The exploration of Computronium and causality engines is more than science fiction. It is a speculative journey into the far reaches of physical law and technological possibility. It invites us to reconsider the relationship between matter, energy, and information, to envision a cosmos where intelligence itself becomes a force-shaping reality. While we are only at the beginning of such explorations, the questions these ideas raise about the ultimate potential of matter, computation, and time suggest that the universe may hold forms of power and energy that are, for now, beyond imagination, but not beyond reason. These concepts compel us to think about a future in which advanced civilizations might not only harness stars and black holes, but also manipulate the very structure of matter and time to achieve levels of energy control that seem godlike by today's standards. In this realm of thought, energy is no longer simply a property of mass or motion. It is a product of computation, a derivative of information, and a reflection of the flow of time itself. Computronium collisions and causality engines together represent a vision of the universe in which the boundaries between physical, informational, and temporal phenomena dissolve. This is a universe where the very essence of reality is malleable, where the interplay of matter, computation, and time could produce events of extraordinary scale and complexity, and where civilizations capable of mastering these forces would operate at a level of understanding and power far beyond our current reach.